Hello there, and welcome. Tonight I want to take you somewhere. Somewhere that exists not in the maps we know or the atlases we've drawn, but in a quiet corner of imagination where the impossible becomes gently possible, where the rules we take for granted soften like wax near a warm flame, and where the universe itself seems to breathe differently. I want to take you to a place where the smallest things we know become as large as the moon that hangs outside your window right now, if you're lucky enough to see it, or that you remember from nights when the sky was clear and the world felt infinite. This is not a journey that requires you to pack anything or prepare in any special way. All you need is exactly what you have right now, your presence, your breath, perhaps the darkness around you, and a willingness to let your mind drift like a boat untethered from its dock, floating on calm waters toward horizons we haven't yet imagined. You see, we live in a universe of scales so vast and so minute that our minds, evolved as they were to navigate the middle ground of trees and rivers and mountains, can barely grasp the extremes. On one end, we have the cosmic scale, the realm of galaxies separated by millions of light years, clusters of stars so numerous that counting them would take lifetimes upon lifetimes, black holes whose gravity bends space and time into shapes we can only describe with mathematics. And on the other end, far below the threshold of our vision, below even what the most powerful microscopes can show us directly, there exists another realm entirely, the quantum world, where particles smaller than atoms dance according to rules that seem to mock our everyday understanding of how things should behave. These particles, with names like electrons and quarks and photons, are so small that if an atom were enlarged to the size of a cathedral, the nucleus at its heart would still be no larger than a fly, and the electrons orbiting it would be specks of dust caught in the cathedral's vast empty space. Tonight, though, I want to invite you to imagine something different, something that at first might sound impossible, even a little strange, but the more we sit with it, the more it gently opens into wonder. What if these quantum particles, these impossibly tiny building blocks of everything we see and touch and are, what if they were not small at all? What if, in some other universe, in some other version of reality that we can visit tonight in our minds, quantum particles were the size of moons? Not metaphorically, not symbolically, but literally, massive spheres of quantum possibility hanging in the night sky, obeying the same strange quantum rules, but on a scale we could see with our naked eyes, feel with our whole bodies, experience as a tangible presence in our world. I know what you might be thinking as you lie there in the darkness or sit, in your comfortable chair, perhaps with a cup of tea cooling beside you, or a blanket pulled up to your chin. You might be thinking that this could never happen, that the laws of physics as we understand them wouldn't allow such a thing, that quantum effects only manifest at the smaller scales and disappear as objects grow larger. And you'd be right, in our real universe, with the physics we've discovered through centuries of careful observation and experimentation. But tonight, just for these next few hours, we might let our imagination drift somewhere else, somewhere where the rules are different, where the impossible becomes a gentle playground for our curiosity. Because sometimes, in exploring what cannot be, we discover new ways of understanding what is. Let me tell you a little bit about where you and I are right now, in this moment we're sharing across space and maybe across time. I'm speaking to you from a quiet place, and you're listening from wherever you are in the world. Maybe it's late at night where you are, and the house has settled into that particular silence that only comes after midnight, when even the walls seem to be sleeping. Or perhaps it's early morning, that liminal time before the world fully wakes, when the light is still grey and uncertain. I'm curious about where you are as you listen to this. Are you in a city where the lights never quite go out, where even now you can hear the distant hum of traffic or the occasional siren? Or are you somewhere rural, where the darkness is thick and complete, where the stars, if you were to look outside, would be scattered across the sky like spilled salt on a black tablecloth? Whatever time it is where you are, whatever corner of our planet you're listening from, I want you to know that you're part of something beautiful right now. You're part of a long tradition of humans who have looked up at the night sky and wondered, who have asked questions that have no easy answers, who have let their minds wander into territories that maps cannot chart. And if this kind of journey, this gentle exploration of cosmic mysteries, feels like something you'd want to return to, if you find yourself settling into this space we're creating together like settling into a warm bath, then perhaps you might want to subscribe or follow along so we can meet here again under the stars, real or imagined, and continue our conversations about the universe and our place in it. Think of it less as a subscription and more as a bookmark in the infinite library of wonder, a way to find your way back to this quiet corner where questions matter more than answers and where the impossible is always welcome. But let's return to our thought experiment, to this universe we're imagining where quantum particles have swelled to the size of moons. To understand what this might mean, we need to first understand scale itself, that invisible ladder that connects the tiniest things to the largest. Right now, as you lie there, or sit there, you exist at what we might call the human scale. Your body is measured in feet or meters, your lifetime in decades, your daily experience in hours and minutes. This is the scale at which water feels wet, at which gravity means things fall down, at which solid objects stay solid and don't suddenly appear on the other side of walls. It's a comfortable scale, one evolution has prepared us for, one where our intuitions generally serve us well. But venture away from this human scale in either direction, and things begin to get strange. Go larger, and you encounter distances so vast that light itself, the fastest thing we know, takes years to traverse them. The nearest star to our Sun, Proxima Centauri, is over 4 light-years away, which means if you were to travel at the speed of light, it would still take you 4 years to get there. Our galaxy, the Milky Way, is about 100,000 light-years across, containing hundreds of billions of stars, each potentially with its own planets, its own possibilities for wonder. And our galaxy is just one among billions in the observable universe, scattered across space like islands in an ocean that has no shores. Now go in the other direction, toward the small, and things become equally mind-bending. A typical atom is about 1/10,000,000,000th of a meter across. To put that in perspective, if you were to line up atoms edge to edge, you would need about 10 million of them to span the width of a single millimeter. And atoms themselves are mostly empty space. If the nucleus of an atom were a marble in the center of a football stadium, the electrons would be like gnats buzzing around the outer walls, and those electrons, those fundamental particles that give atoms their chemical properties, they don't even have a definite size in the way we usually think of size. They exist as clouds of probability smeared out in space, more like ideas than objects. This is the realm where quantum mechanics reigns, where particles can be in multiple places at once, where observing something changes it, where particles separated by vast distances can remain mysteriously connected. It's a realm that physicists have been exploring for over a century, and yet it still surprises us, still challenges our most basic assumptions about reality. The equations work perfectly, the predictions match experiments to extraordinary precision, and yet when we try to translate what the mathematics is telling us into everyday language, into images and metaphors we can grasp, we find ourselves speaking in paradoxes and contradictions. So what would happen if we took these quantum rules, these strange behaviors that normally only manifest at the scale of atoms and smaller, and we scaled them up to the size of moons? What if, instead of electrons being probability clouds around atomic nuclei, we had moon-sized probability clouds orbiting planet-sized centers? What if the quantum uncertainty that makes it impossible to know both the exact position and momentum of an electron applied to objects we could see in our night sky? What if entanglement, that spooky connection between particles that Einstein couldn't quite accept, linked moons on opposite sides of the sky? This is the universe we're going to explore together tonight, not because it could exist in reality, but because imagining it might help us understand our own universe better. Sometimes, to truly see something, we need to imagine it transformed, enlarged, made strange. It's like how you might not notice the pattern of your breathing until someone asks you to pay attention to it, and suddenly you're aware of each inhale and exhale, of the rhythm that's been keeping you alive all this time without your conscious participation. In the same way, by imagining quantum particles as moons, we might begin to notice things about the quantum world and about our regular world that we've been taking for granted. As we prepare to dive deeper into this thought experiment, I want you to take a moment to notice where you are right now, not just geographically, but experientially. Notice the weight of your body wherever it's resting, the temperature of the air on your skin, the sounds around you, whether they're the sounds of civilization or nature, or just the subtle noises of your own body, your breathing, your heartbeat if you listen closely enough. Notice how, even in the darkness, if you're in darkness, there are different shades and textures to the black. how your eyes create patterns and colours even in the absence of light. This is you, existing at human scale, experiencing the universe through senses evolved for survival on the African savannah, trying to comprehend scales and phenomena that no human ancestor could have imagined. And yet here you are, capable of imagining atoms and galaxies, capable of following the mathematics of quantum mechanics even if you don't know the equations, capable of wondering about things that have no practical impact on your daily life, but that somehow feel important anyway. This capacity for wonder, this ability to ask what if, and follow the question wherever it leads, this might be one of the most beautiful things about being human. We're not content to just exist in the universe. We want to understand it, to imagine it differently, to play with it in our minds like a child plays with blocks, building and rebuilding, creating new patterns and possibilities. In our imagined universe, the one we're about to explore more deeply, the moon outside your window, if you have one, wouldn't be a solid rock orbiting Earth at a fixed distance. Instead, it might be a vast quantum probability cloud, existing in many possible positions at once until someone observes it, at which point it would choose a specific location, only to become uncertain again once the observation ends. The tides wouldn't follow a predictable pattern based on gravitational pull, but would instead fluctuate based on quantum probabilities, sometimes high, sometimes low, sometimes both at once until the moment of measurement. The night sky wouldn't show fixed constellations, but rather shifting patterns of probability, interference patterns created by the overlapping wave functions of quantum moons, beautiful and ephemeral, never quite the same twice. I realise this might sound bizarre, even unsettling, but I want to assure you that in our imagined universe, these quantum effects wouldn't be chaotic or frightening. They would be gentle, like the way fog moves through a valley, or the way thoughts drift through your mind as you're falling asleep. The quantum moons wouldn't suddenly appear and disappear with jarring discontinuity, but would instead fade in and out like breathing, like the slow pulse of bioluminescent waves on a quiet beach. This would be a universe of soft edges and gentle uncertainties, where nothing is quite solid but everything is somehow still reliable, still beautiful, still worthy of wonder. Think about how we already live with uncertainty in our daily lives, how we navigate probabilities without even realizing it. When you set out to meet a friend, you don't know exactly what will happen, what you'll talk about, how you'll feel, but you go anyway, trusting in the general shape of the experience, even if the details remain uncertain. When you plant a seed, you don't know exactly how the plant will grow, which direction each branch will take, how many leaves it will have, but you trust in the general process, in the probability of growth given the right conditions. Our imagined quantum moon universe would simply make this uncertainty more visible, more explicit, more beautiful in its honesty about the fundamental indefiniteness that underlies all existence. As we continue on this journey together, we'll explore what it might mean for gravity to interact with these moon-sized quantum objects, how galaxies might form from probability clouds rather than solid matter, what it might be like to live on a planet orbiting a quantum star, to evolve consciousness in a universe where uncertainty isn't hidden at microscopic scales but displayed across the sky every night. We'll consider how the different interpretations of quantum mechanics, Copenhagen, many worlds, pilot waves and others, might manifest differently when the quantum effects are so large we can see them. We'll imagine what art and science and philosophy might look like in such a universe, how beings who grew up with visible quantum effects might think differently about identity, about choice, about the nature of reality itself. But we'll also keep coming back to our own universe, to the real quantum effects that surround us even if we can't see them. We'll talk about how quantum mechanics underlies the chemistry that makes life possible, how quantum tunneling allows the sun to shine, how quantum entanglement might one day enable unbreakable encryption or instantaneous communication across vast distances. We'll explore how the same rules that would govern our imaginary moon-sized quantum particles actually do govern the real particles that make up everything around us, including our own bodies. We'll find that the wonder we feel imagining giant quantum moons is just a reflection of the wonder we should feel, knowing that we ourselves are quantum beings, collections of particles obeying the same strange rules, just at a scale too small for our senses to detect directly. The gentle truth is that we already live in a quantum universe. Every atom in your body, every photon of light entering your eyes, every electron flowing through the device you're using to listen to this. They all exist in quantum superposition until measured. They all have wave-like properties. They can all become entangled with other particles. The only difference between our real universe and our imagined one is scale. And scale, when you think about it, is just a number, just a relationship, just a way of comparing one thing to another. In the grand scheme of the cosmos, the difference between an electron and a moon might be less significant than we imagine. Both are just collections of energy and information, patterns in the quantum fields that underlie all reality, temporary arrangements in the endless dance of existence. As you lie there or sit there, letting these ideas wash over you like gentle waves, I want you to remember that confusion is okay, that not understanding everything is not only acceptable, but beautiful. The universe doesn't require us to understand it completely in order to exist, and we don't need to grasp every detail of quantum mechanics to appreciate its mystery and beauty. Sometimes the best approach is to simply let the ideas flow through us, to feel their texture and temperature without trying to hold them too tightly. Like trying to hold water in your hands, the harder you squeeze, the more it escapes. But if you cup your hands gently, if you create a soft container, the water can rest there for a moment, clear and still, reflecting the sky. This is how I want you to approach our journey tonight. With gentle, cupped hands, ready to hold wonder without grasping, ready to explore without conquering, ready to imagine without needing to believe. We're not trying to convince ourselves that quantum particles really could be the size of moons in our universe. We're simply using our imagination as a tool, a lens, a way of seeing the familiar from an unfamiliar angle. It's like looking at your own city from an airplane window and suddenly seeing patterns and connections you never noticed from the ground. The city hasn't changed, but your perspective has. And with that new perspective comes new understanding, new appreciation, new questions you didn't even know you wanted to ask. Speaking of questions, I'm curious about you, about who you are and where you are as we share this moment. Are you someone who has always been fascinated by space? Who grew up reading about black holes and galaxies, watching documentaries about the cosmos? Or are you new to these ideas, drawn here perhaps by curiosity, or by the promise of a gentle voice in the darkness, a bedtime story for grown-ups who still wonder about the universe? Are you a scientist yourself, smiling perhaps at my simplifications, appreciating the attempt to make the complex accessible? Or are you someone who usually avoids science, who found it intimidating in school, but is discovering now that it can be beautiful when approached with poetry rather than equations? Whatever brought you here, whoever you are, wherever you're listening from, you're welcome in this space. There's no prior knowledge required, no test at the end, no wrong way to imagine what we're imagining together. If you find your mind wandering, that's perfect. Let it wander. If you fall asleep before we're finished, that's beautiful too. Your dreams might take you places even stranger and more wonderful than the universe we're imagining. And if you find yourself wide awake, fascinated, wanting to know more, that's equally welcome. There's room here for all responses, all ways of being present with these ideas. As we prepare to move deeper into our exploration, to really examine what it would mean for quantum particles to be moon-sized, I want to take a moment to appreciate the actual moon, if you can see it, or to remember it if you can't. Our moon, Earth's companion for billions of years, the silent witness to the entire history of life on our planet, from the first simple cells to the complex ecosystems we see today, including us, including this moment we're sharing. The moon has been there through it all, pulling our tides, stabilizing our axis, giving our ancestors a calendar and our poets a metaphor. It's about 384,000 kilometers away, close enough that we've walked on it, far enough that it takes light more than a second to travel between us. Now imagine if that moon weren't a solid sphere of rock, but instead a quantum probability cloud, a massive electron-like object orbiting Earth, according to quantum rather than classical rules. It wouldn't have a definite position, but rather a probability distribution, perhaps concentrated where we usually see the moon, but with a non-zero chance of being anywhere in its orbital range. On most nights, you might see it as a fuzzy, luminous cloud, brightest at its most probable position, but with wisps and tendrils extending in all directions, like a cosmic jellyfish made of light and possibility. Sometimes, when conditions were just right, you might see interference patterns as the moon's wave function interfered with itself, creating rings and spirals of light and darkness across the sky. a natural aurora of pure quantum probability. The tides in such a world wouldn't follow the regular pattern we know, but would instead fluctuate based on where the moon's probability was concentrated at any given moment. Most of the time, the tides would be similar to what we experience, but there would be variations, unexpected high tides when the moon's wave function happened to collapse closer to Earth, unusual low tides when it collapsed farther away. Coastal communities would have to adapt to this uncertainty, perhaps developing a more flexible, probabilistic relationship with the sea, accepting that some things cannot be predicted precisely, but only understood in terms of likelihoods and possibilities, and this is just one moon in our imagined universe. Think of Jupiter with its dozens of moons, each one a quantum object, their wave functions overlapping and interfering with each other, creating complex patterns of probability around the giant planet. Or Saturn's rings, which in our universe are made of countless small pieces of ice and rock, but in our quantum universe might be standing waves of probability, quantum resonances that create stable patterns without any solid material at all. The entire solar system becomes a symphony of wave functions, each celestial body singing its own quantum song, harmonizing and interfering with the others in endlessly complex patterns. But I'm getting ahead of myself, carried away by the beauty of what we're imagining. Let's slow down, take a breath, and prepare to explore this idea more systematically, more carefully, though never losing the sense of wonder that makes the exploration worthwhile. In the next part of our journey, we're going to look more closely at what it means to change scale, to take something tiny and make it huge, or to take something huge and make it tiny. We'll explore how the laws of physics change or don't change with scale, why quantum effects usually disappear at large scales in our universe, and what would have to be different for them to persist at the scale of moons. We'll also begin to explore the different quantum phenomena that would become visible in our imagined universe. Superposition, where objects exist in multiple states simultaneously. Entanglement, where distant objects remain mysteriously connected. Tunneling, where objects pass through barriers they shouldn't be able to cross. And the uncertainty principle, which says we can never know everything about a quantum system at once. Each of these phenomena, currently hidden at microscopic scales, would become a visible part of daily life in our moon-sized quantum universe, as obvious and undeniable as sunrise and sunset. As we continue, remember that you can engage with these ideas at whatever level feels comfortable. If you want to simply let the words wash over you, enjoying the rhythm and the imagery without worrying about understanding every concept, that's perfectly fine. If you want to pause and think deeply about each idea, to really try to visualize what we're describing, that's wonderful too. And if you find yourself drifting between attention and inattention, between understanding and confusion, between waking and sleeping, that liminal state might actually be the perfect place from which to explore these liminal ideas, these concepts that exist at the boundary between the possible and the impossible, between science and imagination, between what is and what might be. The universe, both the real one and our imagined one, is patient. It has been here for billions of years before us and will be here for billions of years after. It doesn't rush, doesn't insist, doesn't demand understanding. It simply is, in all its quantum uncertainty and classical definiteness, in all its microscopic strangeness and macroscopic familiarity, in all its mathematical precision and poetic ambiguity. And tonight, we have the privilege of playing in this universe with our minds, of asking what if, and following the question into territories that no map has charted, that no experiment could test, but that might nevertheless teach us something true about the nature of reality and our place within it. So settle in, get comfortable, let your breathing slow and deepen, and prepare to journey with me into a universe where the impossible becomes possible, where the invisible becomes visible, where quantum particles swell to the size of moons and hang in our sky like luminous questions, forever asking us to reconsider what we think we know about the nature of existence. This is our starting point, our launch pad into wonder. The real journey is about to begin. Now that we've settled into this space together, into this gentle exploration of impossible possibilities, let's begin to truly understand what we're imagining when we talk about quantum particles the size of moons. To do this, we need to take a journey through scale itself, that invisible architecture that organizes the universe from the unimaginably small to the incomprehensibly large. Scale isn't just about size, you see. It's about the relationships between things, about how the laws of physics manifest differently at different levels of reality, about how what seems solid and permanent at one scale reveals itself to be mostly empty space at another, how what appears random and chaotic at one level emerges as pattern and order when we step back far enough to see the whole picture. Let's start with something familiar, something you can relate to directly: your own hand. Hold it up if you can, or simply imagine it if you're too comfortable to move. Your hand is about 20 centimeters long, perhaps a bit more, perhaps a bit less. It's made of skin and bone and muscle and blood, all organized into this remarkable tool that can write symphonies and caress loved ones and build cities and paint sunsets. At the scale of daily human experience, your hand is a solid, definite object with clear boundaries. You know where it ends and the rest of the world begins. You can move it through space in smooth, continuous motions. It obeys the laws of classical physics that Newton described. When you push something with it, the thing moves. When something pushes back, you feel it. When you let go of an object, it falls. But now let's zoom in. Let's shrink our perspective down to the scale of the cells that make up your hand. Each cell is roughly 10 micrometers across, which means you could line up about 100 of them across the width of a millimeter. At this scale, your solid hand reveals itself to be a vast city of individual living units, each one a complete factory of biological machinery, taking in nutrients, producing energy, manufacturing proteins, dividing to create new cells, dying when their time comes. The boundaries that seemed so clear at the human scale become fuzzy at the cellular scale. Where exactly does one cell end and another begin? The membranes that separate them are not walls, but rather dynamic, permeable barriers, constantly exchanging materials and information. Let's zoom in further, down to the scale of molecules. Now we're talking about nanometers, billionths of a meter. The DNA in your cells, if stretched out, would be about 2 nanometers wide but up to 2 meters long, all coiled and packed into a nucleus that's only about 10 micrometers across. At this scale, the solid matter of your hand becomes even less solid. Molecules are constantly in motion, vibrating, rotating, bumping into each other. The proteins that give your muscles their strength are long chains of amino acids, folded into precise shapes that allow them to grab and release, to contract and relax. The water molecules that make up most of your body's mass are tumbling and sliding past each other billions of times per second. What seemed permanent and stable at the human scale is revealed to be a constant dance of molecules, a dynamic equilibrium rather than a static structure. And now, let's take the final plunge down to the scale of atoms and subatomic particles. An atom is about 1/10,000,000,000th of a meter across, but as we mentioned earlier, it's mostly empty space. If the nucleus of an atom in your hand were enlarged to the size of a grape and placed at the center of a cathedral, the electrons would be like specks of dust orbiting in the vast empty space of the cathedral. And those electrons, they don't even orbit in the way planets orbit the sun. They exist as probability clouds, smeared out in space, more like standing waves than particles. The quantum mechanical description of an electron doesn't tell us where it is, but rather where we might find it if we look. Until we make a measurement, the electron exists in a superposition of all possible positions weighted by their probabilities. This is the scale where quantum mechanics reigns supreme, where the classical physics that works so well for your hand as a whole breaks down completely. At this scale, particles can tunnel through barriers that they shouldn't be able to cross according to classical physics. They can be entangled with other particles, maintaining instantaneous correlations regardless of the distance between them. They exist in superposition until observed, at which point they collapse into definite states. The uncertainty principle governs this realm, telling us that we can never know both the position and momentum of a particle with perfect precision. The more accurately we know one, the less accurately we can know the other. Now you might wonder why, if the atoms in your hand obey quantum mechanics, your hand as a whole seems to obey classical physics. Why don't you see your hand in superposition, existing in multiple places at once? Why can't your hand tunnel through walls? Why doesn't your hand become entangled with objects across the room? The answer lies in something called decoherence, and in the way quantum effects tend to average out when you have enormous numbers of particles interacting with each other and with their environment. Your hand contains something like 1027 atoms, an unimaginably large number. When that many quantum objects interact, their individual quantum properties tend to cancel out, leaving only the average classical behavior that we observe at the human scale. Think of it like this. Imagine you're looking at the ocean from an airplane. From that height, the surface looks smooth, perhaps with some gentle swells. You can't see the individual waves, the foam, the turbulence that you know exists at the surface. As you descend, you begin to see texture, patterns, waves. Get close enough, and you can see individual waves, each one unique, each one unpredictable in its details, even though the overall statistical behavior of waves is well understood. Get even closer, down to the scale of water molecules, and the very concept of a wave breaks down. There are just molecules moving, colliding, exchanging energy. The wave is an emergent phenomenon, a pattern that arises from the collective behavior of countless individual particles. This is how our universe is structured. Different phenomena emerge at different scales, and what's true at one scale may not be true at another. The laws of thermodynamics emerge from statistical mechanics. Chemistry emerges from quantum mechanics. Biology emerges from chemistry. Psychology emerges from neurobiology. Each level has its own rules, its own patterns, its own forms of organization, even though they are all ultimately grounded in the quantum mechanical behavior of fundamental particles. But what if this weren't the case? What if quantum effects didn't decohere at large scales? What if the strange behaviors we see in individual atoms and electrons also appeared in objects the size of moons? This is the thought experiment we're exploring, and to understand its implications, we need to think carefully about what would have to be different about the laws of physics for this to be possible. In our universe, there's a characteristic scale called the de Broglie wavelength that determines when quantum effects become important. For any object, this wavelength is inversely proportional to the object's momentum. For a typical electron moving at typical speeds, the de Broglie wavelength is about the size of an atom, which is why electrons exhibit obvious wave-like behavior at atomic scales. For a baseball thrown at 100 miles per hour, the de Broglie wavelength is about 10 to the 34 meters, far smaller than any measurement we could ever make, which is why baseballs seem to follow classical trajectories rather than quantum ones. For a moon-sized object to exhibit quantum behavior, its de Broglie wavelength would need to be comparable to or larger than its size. Given the enormous mass of a moon, this would require either incredibly slow speeds, approaching absolute stillness, or a fundamental change in the constants of nature that determine the relationship between mass, momentum, and wavelength. In our imagined universe, let's suppose that the latter is true. The fundamental constants are different in such a way that massive objects can have large de Broglie wavelengths even when moving at ordinary speeds. This change would ripple through all of physics. Gravity would interact with quantum wave functions in ways we've never observed. The formation of stars and planets would proceed differently. Chemistry might not work the same way, or might not work at all. Life as we know it might be impossible. But let's not worry about making everything consistent. We're not trying to design a real universe that could actually exist. We're using our imagination to explore ideas, to see familiar concepts from new angles, to appreciate the strange beauty of quantum mechanics by scaling it up to sizes we can visualize. So in our imagined universe, moons are quantum objects with de Broglie wavelengths comparable to their size. What would this look like? Well, first of all, a quantum moon wouldn't have a definite position. Instead, it would exist as a probability cloud, dense in some regions and thin in others. The densest region would correspond to the moon's most probable position, where you'd be most likely to find it if you measured its location. But there would always be some probability, however small, of finding it elsewhere in its orbital range, or even beyond. Imagine looking up at the night sky in this universe. Instead of a sharp, circular moon, you'd see a diffuse glow, brightest at the center but fading gradually into the darkness. On some nights, the probability cloud might be tightly concentrated, and the moon would appear almost as definite as our familiar moon. On other nights, the cloud might be more spread out, and the moon would appear as a vast, faint haze covering much of the sky. The shape of the cloud would depend on the moon's quantum state, which would evolve over time according to the Schrödinger equation, the fundamental equation of quantum mechanics. But it gets even stranger. In quantum mechanics, particles don't just have indefinite positions, they can exist in superposition of different states. An electron can be spin up and spin down at the same time. A photon can be horizontally and vertically polarized simultaneously. In our imagined universe, a moon could be in multiple places at once, not just spread out in a probability cloud, but actually existing in a superposition of distinct positions. You might look up and see not one fuzzy moon but several, each one translucent, each one real and not real at the same time, like multiple exposures on a single photograph. These multiple moons wouldn't be independent. They'd be different components of a single quantum wave function, and they'd interfere with each other in the way that waves interfere. Where the peaks of two component waves align, you'd see bright regions of constructive interference. Where peaks meet troughs, you'd see dark regions of destructive interference. The night sky would be painted with interference patterns, ripples and rings of light and shadow that would shift and evolve as the moon's wave function changed over time. And what about measurement? In quantum mechanics, measurement causes the wave function to collapse from a superposition of states to a single definite state. But what would it mean to measure a moon-sized quantum object? Would looking at it with your eyes be enough? Would you need sophisticated scientific instruments? Would the moon's interaction with sunlight constitute a measurement? These are deep questions, even for microscopic quantum systems, and they become even more profound when we scale up to astronomical sizes. Let's imagine that in our universe, casual observation isn't enough to collapse the wave function of a quantum moon. Looking at it with your naked eyes, you'd see the superposition, the interference patterns, the quantum uncertainty in all its glory. But if you pointed a telescope at it, if you tried to measure its position precisely, the act of measurement would cause the wave function to collapse. Suddenly, the multiple translucent moons would converge into one, the probability cloud would condense to a point, and for a moment, you'd see a sharp, definite moon like the one we know. But as soon as you stopped measuring, as soon as you looked away, the moon would begin to spread out again, returning to its quantum superposition. This would make astronomy a very different endeavour in our imagined universe. Astronomers wouldn't just be passive observers but active participants in determining the state of celestial bodies. The act of observation would literally change what was being observed. There might be debates about whether it was ethical to collapse the wave function of a quantum moon, to force it from its natural superposition into a definite state. Some might argue that the moon should be left in its quantum state, that we should learn to appreciate the beauty of uncertainty rather than always trying to pin things down to definite values. Navigation would also be challenging in such a universe. You couldn't rely on the moon being in a specific place at a specific time. Instead, you'd have to work with probabilities. There's a 70% chance the moon will be in the eastern sky tonight, a 20% chance it'll be in the west, and a 10% chance it'll be somewhere else entirely. Sailors would need to be comfortable with uncertainty, ready to adapt their course based on where the moon's wave function happened to be concentrated on any given night. But perhaps the most profound difference would be in how the inhabitants of such a universe thought about reality itself. In our world, we grow up with the assumption that things have definite positions, that objects exist in specific places even when we're not looking at them. This seems so obvious that we rarely question it. But in a universe where moon-sized objects exist in quantum superposition, where you can see with your own eyes that things don't have definite positions until measured, you'd grow up with a fundamentally different intuition about the nature of reality. Children in such a universe might play games with the uncertainty, trying to predict where the moon's probability cloud would be thickest, making wishes on interference patterns instead of shooting stars. Artists might paint the multiple moons in their superposed states, capturing the beauty of uncertainty on canvas. Poets might write about the moon that is and isn't, the moon that exists everywhere and nowhere, the moon that becomes definite only when observed, like thoughts that crystallize only when we try to express them in words. The science of such a universe would also develop differently. Quantum mechanics wouldn't be a strange theory that contradicts our everyday experience. It would be the obvious description of how things work, visible every night in the sky. Classical mechanics, with its assumption of definite positions and trajectories, might be the strange, abstract theory, applicable only to the rare cases where decoherence is complete and quantum effects have averaged out. Students might struggle to understand how anything could have a definite position, just as our students struggle to understand how particles can be in superposition. Let me paint you a more detailed picture of what a night might be like in this quantum moon universe. You step outside your dwelling as the sun sets, and the sky gradually darkens from blue to purple to black. The stars begin to appear, but they're not points of light as we know them. Each star is a quantum object, its light spread out in probability clouds, creating a sky that looks more like a vast watercolor painting than a field of distinct points. The brightest stars have the most concentrated probability clouds, appearing almost point-like, while dimmer stars are spread out into glowing patches that overlap and interfere with each other. As the sky darkens further, the moon begins to rise, but it doesn't emerge from the horizon as a distinct disk. Instead, there's a gradual brightening in the eastern sky, a probability tide rising from the Earth's edge. At first, it's just a faint glow, barely distinguishable from the background sky. But as more of the moon's wave function rises above the horizon, the glow intensifies and begins to show structure. You see ripples and waves in the brightness, interference patterns created by different components of the moon's quantum state. On this particular night, the moon is in a superposition of 3 primary positions, each about 30 degrees apart in the sky. You see 3 overlapping glows, each one translucent, each one showing the familiar features of the lunar surface, but from slightly different angles. Where the 3 components overlap, the light is brightest. Where they interfere destructively, there are dark bands cutting across the sky. The whole display slowly shifts and evolves as the moon's wave function propagates according to quantum mechanics, the 3 components rotating around each other in a cosmic dance of probability. You lie down on the grass to better take in the spectacle, and as you watch, you notice smaller effects. There are quantum fluctuations in the brightness, random variations as virtual particles pop in and out of existence in the moon's quantum field. There are occasional flashes as cosmic rays interact with the moon's wave function, causing momentary partial collapses that quickly spread out again. And if you watch carefully, you can see the tidal effects on the moon's wave function caused by Earth's gravity, a subtle stretching and squeezing of the probability cloud that creates its own patterns in the sky. The moonlight itself is different in this universe. It's not the steady white light we know, but rather a flickering, uncertain illumination that varies from moment to moment as the moon's wave function evolves. Shadows are not sharp, but fuzzy, with edges that shift and blur. The landscape around you seems to breathe with the quantum uncertainty of the moon, everything slightly indefinite, everything participating in the cosmic uncertainty that defines this universe. You might wonder how life could evolve in such a universe, how organisms could navigate and survive when even the basic facts of celestial mechanics are uncertain. But life is remarkably adaptable, and in our imagined universe, organisms would have evolved to work with quantum uncertainty rather than against it. Perhaps they would have quantum sensors that could detect probability clouds directly. Perhaps they would use quantum entanglement for navigation, maintaining entangled particles that would allow them to sense the quantum state of distant objects. Perhaps photosynthesis would work differently, adapted to the flickering, uncertain light of quantum stars and moons. Plants might have leaves that adjust their quantum state to match the incoming light, creating interference patterns that maximize energy absorption. Animals might have eyes that can see superposition directly, processing multiple possible states simultaneously and only collapsing them to definite values when necessary for decision-making. Predators and prey might engage in quantum hide-and-seek, manipulating their own wave functions to become more or less definite, more or less localized, depending on the situation. Human consciousness itself might be different in such a universe. If you grew up seeing superposition and uncertainty every day, your brain might develop different ways of processing information. Perhaps you would be more comfortable with ambiguity, more able to hold multiple contradictory ideas in your mind simultaneously. Perhaps decision-making would be less about choosing one option and more about adjusting the probability weights of different options, maintaining superposition until the last possible moment. The technology of such a civilization would also be fascinating to imagine. Without solid, definite matter to work with, how would you build structures? Perhaps buildings would be quantum standing waves, stable patterns in probability fields that provide shelter without being solid in the classical sense. Transportation might involve manipulating your own wave function to increase the probability of being where you want to go, a kind of quantum tunneling on a macroscopic scale. Communication might use entanglement, with instantaneous correlation between entangled moons allowing for faster-than-light information transfer, though still constrained by the no-communication theorem that prevents true faster-than-light messaging. But let's not get too far ahead of ourselves. We're still exploring the basic implications of moon-sized quantum particles, still trying to wrap our minds around what it would mean for such massive objects to exhibit quantum behavior. The key insight is that scale matters in our universe in a way that it wouldn't in our imagined universe. In our reality, quantum effects are confined to the microscopic realm, not because of any fundamental law, but because of the practical consequences of decoherence and the relationships between fundamental constants. Change those constants, prevent decoherence, and suddenly the quantum world could be as visible and tangible as the classical world we experience every day. This thought experiment helps us appreciate just how strange and wonderful quantum mechanics really is. We've become accustomed to hearing about quantum effects in abstract terms, about particles we'll never see doing things we can barely imagine. But by scaling these effects up to moon size, by imagining them painted across the night sky, we can begin to feel their strangeness in a more visceral way. The moon in superposition isn't just a mathematical abstraction, but something you could see with your own eyes, something that would affect the tides and the light and the very rhythm of life on Earth. As we continue to explore this imagined universe, we'll dive deeper into specific quantum phenomena. We'll explore what happens when these moon-sized quantum particles interact with each other, how entanglement would manifest at astronomical scales, what quantum tunneling would look like when the barriers are planetary orbits rather than atomic energy levels. We'll consider how gravity, that most classical of forces, would behave in a universe where massive objects don't have definite positions. We'll imagine what the cosmic web of galaxies would look like if it were woven from quantum probability clouds rather than classical matter distributions. But for now, let's simply rest in the strangeness of scale itself, in the recognition that size is not just a number, but a determining factor in how physics manifests. The universe looks different at every scale, from the quantum foam at the Planck length to the vast voids between galaxy clusters. Each scale has its own beauty, its own complexity, its own mysteries. By imagining quantum effects at the scale of moons, we're not just playing a game of what if. We're exploring the deep structure of reality, the hidden connections between the very small and the very large, the quantum and the classical, the uncertain and the definite. In our next chapter, we'll focus specifically on superposition, on what it means for an object to exist in multiple states simultaneously, and how this most mysterious of quantum phenomena would manifest if it occurred at the scale of moons. We'll explore the mathematics and the philosophy, the practical implications and the poetic possibilities. But for now, as this chapter draws to a close, I want you to simply hold in your mind the image of a quantum moon, spread out across the sky in a probability cloud, neither here nor there but somehow everywhere. A cosmic question mark that challenges our most basic assumptions about what it means for something to exist. There's something beautiful about the way you can hold two thoughts in your mind at once, isn't there? Right now, as you listen to these words, part of you is following the meaning, tracking the ideas as they unfold, while another part might be thinking about something else entirely, perhaps what you'll do tomorrow, perhaps a memory from long ago, perhaps just noticing the comfort of your position or the rhythm of your breathing. This ability to exist in multiple mental states simultaneously, to be here and elsewhere at the same time, is something we take for granted, but it's actually a lovely parallel to one of the most mysterious phenomena in quantum mechanics: superposition. In the quantum world, superposition is not just a metaphor or a mental state, but a fundamental aspect of reality. An electron can spin clockwise and counterclockwise at the same time. A photon can be horizontally and vertically polarized simultaneously. An atom can be excited and unexcited here and there, existing and not existing all at once, until the moment of measurement forces it to choose, to collapse into a single, definite state. This isn't just theoretical abstraction. Scientists have observed superposition countless times in laboratories around the world, have built technologies that depend on it, have won Nobel Prizes for demonstrating its reality. And yet, despite all this evidence, superposition remains deeply counterintuitive, challenging our most basic assumptions about what it means for something to exist. Tonight, in our imagined universe where quantum particles have swelled to the size of moons, we're going to explore what superposition might look like if we could see it with our naked eyes, if it painted itself across the night sky in patterns of light and probability. We're going to imagine moons that exist in multiple places at once, not as copies or illusions, but as genuine quantum superpositions, each component as real as the others, until the moment of observation collapses the whole system into a single state. This is not science fiction, but science imagination, a way of understanding the real by exploring the impossible, of seeing the familiar quantum world from an unfamiliar scale. Let's begin with something simple and build our way up to the cosmic. In our everyday experience, things have definite properties. A coin is either heads or tails, a door is either open or closed, a light is either on or off. We might not know which state something is in, the coin might be hidden under your hand, but we assume it has a definite state whether we're looking or not. This assumption is so fundamental to our thinking that we rarely question it. It's built into our language, our logic, our entire way of navigating the world. But in the quantum realm, this assumption breaks down completely. Before measurement, a quantum coin isn't heads or tails, but both simultaneously, existing in what physicists call a superposition of states. This isn't just uncertainty about which state it's in. It's not that the coin is really heads and we just don't know it. The coin genuinely doesn't have a definite state until measured. It exists in a kind of quantum limbo, a blend of possibilities that only becomes definite when we force it to by observing it. Scientists have demonstrated this with individual particles in countless experiments. The most famous is probably the double-slit experiment, which Richard Feynman called the only mystery of quantum mechanics, because it contains all the weirdness in one simple setup. Send electrons one at a time through two slits, and they create an interference pattern on the detector screen, as if each electron went through both slits simultaneously and interfered with itself. But if you try to detect which slit the electron went through, the interference pattern disappears. The act of measurement forces the electron to choose one slit or the other, destroying the superposition. Now let's scale this up to our moon-sized quantum particles. Imagine standing on Earth, looking up at a quantum moon in superposition. Unlike our familiar moon with its definite position in the sky, this quantum moon exists in multiple locations simultaneously. Perhaps tonight it's in a superposition of 3 positions, one in the eastern sky, one directly overhead, and one in the west. Each component of the superposition has an amplitude, a complex number that determines both the probability of finding the moon in that position if measured and how that component interferes with the others. What would you actually see? Not 3 separate moons exactly, but rather a complex interference pattern created by the overlapping wave functions. Where the waves from different components add constructively, you'd see bright regions. Where they cancel destructively, darkness. The whole sky would be painted with ripples and bands of light, constantly shifting as the moon's wave function evolves according to the Schrödinger equation. It would be like looking at the surface of a pond where 3 stones have been dropped simultaneously. Seeing the overlapping ripples, except these ripples would be 3-dimensional, filling the space above you with probability and light. The mathematics of this is actually quite beautiful, even if we don't need to dive into the equations themselves. Each component of the superposition is described by a wave function, a mathematical object that encodes all the information about that quantum state. When you have multiple components, you add their wave functions together, just like adding waves on water. The total wave function might look like px, eps1 plus beps2 plus s, csec3, where a, b, and c are complex numbers called amplitudes, and vest1, pest2, and vesti3 are the wave functions for the moon being in each of the 3 positions. The probability of finding the moon in any particular position if you measure it is given by the square of the amplitude for that position. But before measurement, all 3 positions are equally real, equally present. The moon isn't secretly in one position with us just being uncertain about which one. It's genuinely in all 3 positions at once, a quantum trinity that only becomes singular when observed. This raises profound questions about the nature of observation and measurement. What counts as a measurement? In the laboratory, scientists use sophisticated detectors to measure quantum particles. But for a moon-sized quantum object, would looking at it with your eyes be enough to collapse the wave function? Would taking a photograph do it? Would the moon's gravitational interaction with Earth constitute a measurement? These questions don't have easy answers even for microscopic particles, and they become even more complex when we scale up to astronomical sizes. Let's imagine that in our universe, casual observation isn't enough to fully collapse the wave function of a quantum moon. Looking at it with your naked eyes, you see the superposition, the interference patterns, the quantum uncertainty in all its glory. But the more precisely you try to measure the moon's position, with telescopes, with laser ranging, with gravitational, wave detectors, the more the wave function collapses toward a definite state. It's as if the universe resists giving up its quantum mysteries, revealing definiteness only under the most insistent interrogation. This would make the night sky a dynamic, ever-changing canvas. As different observers around the world measure the moon with different instruments at different times, they would cause partial collapses of the wave function, creating temporary regions of greater definiteness that would then spread out again into uncertainty. The moon would pulse and breathe with observation, becoming more definite when watched closely, more spread out when left alone. Astronomers would need to coordinate their observations, perhaps establishing quantum quiet zones, where no measurements are allowed, preserving the moon's natural superposition for aesthetic or scientific reasons. But superposition isn't just about position. Quantum objects can be in superposition of any property: energy, angular momentum, polarization, even existence itself. Our quantum moon could be in a superposition of different phases, showing multiple faces simultaneously, full and crescent and new all at once. It could be in a superposition of different compositions, rock and ice and metal existing in the same space, their properties blending in ways that classical physics would never allow. Imagine the tides in such a world. Our ocean tides are caused by the gravitational pull of the moon, stronger on the side of Earth facing the moon and weaker on the opposite side. But if the moon is in superposition, existing in multiple places at once, the tides would respond to all positions simultaneously. You might have 3 or more tidal bulges, one for each component of the moon's position superposition, creating complex patterns of high and low tides that would vary not just with time, but with the quantum state of the moon. Coastal communities would need to develop a completely different relationship with the sea. Instead of simple tide tables predicting high and low tides, they would have quantum tide forecasts, probability distributions for water levels at different times. There's a 40% chance of a high tide at sunset, a 35% chance of a medium tide, and a 25% chance of a low tide, with quantum fluctuations of plus or minus 2 meters. Sailors would need to be comfortable with uncertainty, ready for any possibility, their boats designed to handle the full range of quantum tidal variations. The moonlight itself would be extraordinary in this superposed state. Light from each component of the superposition would interfere with light from the others, creating patterns of constructive and destructive interference. You might see bands of bright moonlight alternating with bands of darkness, slowly shifting across the landscape as the moon's wave function evolves. Colours might appear where different wavelengths interfere differently, creating lunar rainbows that have no classical equivalent. The whole world would be painted with quantum interference, a constantly shifting pattern of light and shadow that would make every night unique. Photography in such a world would be an art form unlike anything we know. A long exposure photograph wouldn't just capture the moon's motion across the sky, but would record the interference patterns of its superposition. You might see beautiful spirals and waves of light, the accumulated probability of the moon's presence over time. Each photograph would be unique, depending on exactly when, during the exposure, various partial measurements occurred, either from the camera itself or from other observers around the world. Photographers might collaborate with astronomers, timing their exposures to coincide with measurements that would create particularly beautiful collapse patterns. Wildlife in this universe would have evolved to deal with quantum superposition as a fact of life. Nocturnal animals might have eyes sensitive to interference patterns, able to navigate by the quantum moonlight. Birds might use the superposition of celestial bodies for navigation, their magnetic sensors detecting not just the Earth's magnetic field, but the quantum state of the moon and stars. Predators and prey might have developed quantum strategies, using the uncertainty to their advantage, hiding in the probability shadows where destructive interference creates darkness. Some creatures might even be able to influence the moon's wave function through their observations. Imagine a species of quantum fireflies whose bioluminescent flashes are bright enough to constitute a measurement of the moon's position. When they flash in synchrony, they could cause a partial collapse of the moon's wave function, temporarily making it more definite. They might use this ability for mating displays, different patterns of flashes creating different collapse patterns in the sky, a cosmic courtship dance that involves the moon itself as a participant. Plants too would be adapted to the quantum light. Their leaves might be structured to capture light from multiple components of the moon's superposition simultaneously, with chlorophyll-like molecules that can exist in their own superposition states to match the incoming quantum light. Photosynthesis might be more efficient in this universe, able to extract energy from the interference patterns themselves, not just from the raw intensity of light. Forests might glow softly at night, their leaves quantum entangled with the moonlight, creating a gentle bioluminescence that ebbs and flows with the moon's quantum state. Human culture in such a universe would be profoundly shaped by visible superposition. Philosophy would develop differently when the question "where is the moon?" doesn't have a simple answer. Children would grow up understanding that things can be in multiple states at once, that reality is fundamentally probabilistic rather than deterministic. This might lead to more flexible thinking, more comfort with ambiguity and paradox, more acceptance of the idea that contradictory things can both be true. Language itself would need to accommodate superposition. We might have verb tenses that indicate quantum states. The moon is and isn't in the eastern sky. She went and didn't go to the market. The tide is probably rising. Grammar would include probability amplitudes, ways of expressing not just what is but what might be, what could be, what exists in superposition until observed. Art in this universe would be extraordinary. Painters might try to capture superposition on canvas, showing multiple states simultaneously in ways that challenge perception. Sculptors might create works that seem to exist in multiple positions at once, using materials that interact with quantum light to create interference patterns. Musicians might compose pieces that mirror quantum superposition, with melodies that exist in multiple keys simultaneously, only resolving to a definite tonality at certain moments, like musical wave function collapse. Science, of course, would be completely different. Quantum mechanics wouldn't be a weird theory that contradicts our intuition, but the obvious description of reality that everyone can see. Children would play with superposition toys, watching small objects exist in multiple states at once. Schools would teach quantum mechanics in kindergarten, using the moon and stars as examples. Classical mechanics, with its assumption of definite states and deterministic evolution, might be the advanced topic, taught only in graduate schools as a limiting case that applies in certain special circumstances. The technology of such a civilization would be based on macroscopic quantum effects. Quantum computers wouldn't need to be kept at near absolute zero to maintain coherence. Room temperature would be fine when quantum effects persist at the scale of moons. Transportation might use quantum tunneling, with vehicles that can pass through barriers by existing in superposition on both sides simultaneously. Communication could use entanglement between quantum moons, allowing instantaneous correlation of information across vast distances. But perhaps the most profound impact would be on our understanding of consciousness and observation. In our world, there's an ongoing debate about the role of consciousness in quantum mechanics. Does consciousness cause wave function collapse, or is consciousness itself a quantum phenomenon? In a universe where you can see superposition with your naked eyes, where your daily experience includes watching wave functions collapse and reform, these questions would be immediate and practical rather than abstract and philosophical. You might notice that your attention affects the quantum moon state, that focusing on one component of the superposition makes it slightly more probable that the collective observation of millions of people can shape the moon's wave function in subtle ways. This wouldn't be mysticism but empirical fact, as measurable as temperature or pressure. Meditation might involve learning to observe without collapsing, to see superposition without forcing it into definiteness. Mental health might include quantum hygiene, practices for interacting with superposed reality in ways that don't create unwanted collapses. As we near the end of this exploration of superposition at cosmic scales, I want to return to the image of you, lying on grass or sand or wherever you've imagined yourself, looking up at a quantum moon in superposition. The moon exists in 3 places at once, and you can see all 3 translucent and overlapping, creating interference patterns that paint the night in ways Van Gogh could never have imagined but might have loved. The tide is coming in, or going out, or both, responding to the moon's multiple positions with its own watery superposition. The air itself seems to shimmer with possibility, with the potential for things to be other than they are. In this moment, you are not just an observer, but a participant in the quantum dance. Your observation, however gentle, influences what you see. The moon's wave function responds to your gaze, perhaps becoming slightly more definite where you focus your attention, slightly more spread out in your peripheral vision. You're entangled with what you observe, part of the same quantum system, the boundary between observer and observed as fuzzy as the moon's indefinite edges. This is the deep lesson of superposition. Whether at the scale of electrons or moons, reality is not as definite as we thought. Things can be multiple ways at once. Contradictions can coexist. The universe is more like a question than an answer, more like a poem than a proclamation. And we, conscious observers in this quantum cosmos, are not separate from this indefiniteness but part of it. Our own thoughts and perceptions existing in superposition until the moment we speak them, write them, act on them. As we prepare to move on to the next aspect of our quantum moon universe, to explore entanglement and the mysterious connections between distant quantum objects, I want you to carry with you this image of superposition made visible. In our real world, electrons and atoms are in superposition all around us all the time, their indefiniteness hidden by scale but no less real. Every atom in your body, every photon entering your eye, every particle in the universe exists in superposition until measured, until forced to choose a single state from among its many possibilities. We live in a quantum universe, whether we can see it or not. The moon-sized quantum particles we've been imagining are just a way of making visible what's already true at scales too small for us to perceive directly. Superposition is not science fiction, but science fact, not a strange exception, but the fundamental rule from which classical definiteness emerges as a special case. By imagining it, at the scale of moons, we're not creating something foreign but revealing something familiar, showing ourselves the quantum reality that underlies everything we thought we knew about the world. The gentle truth is that uncertainty is not a flaw in our understanding but a feature of reality itself. The universe doesn't have definite answers to all our questions because definiteness itself is emergent, approximate, a simplification that works at human scales but breaks down when we look too closely or think too deeply. And perhaps there's something beautiful in this, something liberating in the recognition that reality itself is open-ended, that the future is not determined but genuinely open. That possibility is not just a human concept but a fundamental aspect of existence. As you continue to lie there, watching the quantum moon in its superposed state, you might feel a kind of peace in this uncertainty, a comfort in knowing that the universe itself doesn't always know what it's going to do next, that it too exists in superposition until the moment of decision, the moment of collapse, the moment when possibility becomes actuality. And then, immediately, it begins to spread out again, returning to superposition, returning to possibility, the eternal cycle of definition and indefinition that keeps the universe alive and interesting and full of surprises. Soon, we'll explore how these superposed quantum moons might be connected to each other across vast distances, how entanglement would manifest at cosmic scales, how the mysterious correlations that Einstein called spooky action at a distance would look if we could see them painted across the night sky. But for now, rest in the superposition, in the gentle uncertainty, in the recognition that you too are a quantum being, existing in multiple states at once until the moment you choose, and even then only temporarily, before spreading out again into new possibilities, new superpositions, new ways of being in this endlessly creative cosmos. You know that feeling when you think of someone and moments later they call? Or when two people say the exact same unusual phrase at the same time, despite being rooms or cities apart? We tend to dismiss these as coincidences, and usually they are, but there's something deeply human about sensing connections that transcend ordinary space and time, about feeling linked to distant people and places in ways that logic can't quite explain. Tonight, as we continue our journey through a universe of moon-sized quantum particles, we're going to explore a phenomenon that makes these everyday synchronicities seem mundane by comparison. Quantum entanglement, the strangest and perhaps most beautiful aspect of quantum mechanics, scaled up to cosmic proportions where we can see its mysterious connections painted across the night sky. Entanglement is what happens when quantum particles become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. It's not that they send signals to each other. No information travels between them faster than light. Instead, they exist as a single quantum system, their properties fundamentally linked in a way that space itself cannot sever. Einstein, troubled by this phenomenon, called it spooky action at a distance, and spent years trying to prove it couldn't be real. But experiment after experiment has confirmed that entanglement is not only real, but fundamental to how our universe works at the quantum level. In our world, scientists have created entangled photons, electrons, atoms, even small molecules. They've maintained entanglement across kilometers of optical fiber, between satellites and ground stations, even between particles separated by hundreds of kilometers. The Chinese satellite Mishus has demonstrated entanglement between particles over 1-200 kilometers apart, and there's no theoretical limit to how far entanglement can stretch. Two particles could be entangled across the entire observable universe, their quantum states forever linked despite the cosmic distances between them. But what would entanglement look like if the particles involved were not microscopic but moon-sized? What if you could look up at the night sky and see entangled moons, their quantum states visibly correlated, their properties mysteriously linked across the vast darkness of space? This is what we're going to explore now, and as with superposition, we'll find that scaling up quantum effects doesn't make them less mysterious, but rather reveals their mystery in new and beautiful ways. Imagine two moons, one orbiting Earth and another orbiting Mars, that have become quantum entangled. Perhaps they formed from the same quantum cloud billions of years ago, their wave functions overlapping and intertwining before they separated and found their way to different planets. Or perhaps they became entangled through some cosmic event, a collision with an entangled asteroid or an interaction with the same burst of quantum radiation. However it happened, these two moons are now connected in a way that transcends the hundreds of millions of kilometers between them. From Earth, you look up at your moon, and it appears as we've described, a probability cloud, perhaps in superposition, glowing with quantum uncertainty. But tonight, something special happens. A team of astronomers on Mars makes a precise measurement of their moon's position, collapsing its wave function to a definite location. The instant they do this, and I mean instant, not limited by the speed of light, your moon on Earth responds. If the Mars moon collapses to the northern part of its orbit, Earth's moon instantly becomes more likely to be in the southern part of its orbit. If Mars's moon is measured to be in a high-energy state, Earth's moon instantly shifts to a corresponding low-energy state. You see this happening in real time through your telescope. One moment, Earth's moon is spread out in its usual probability cloud, and the next, without any apparent cause, it suddenly shifts, its wave function changing shape, its interference patterns rearranging themselves. It's as if an invisible hand reached across space and gently squeezed the moon's quantum state into a new configuration. There's no force involved, no energy transferred, just a pure correlation, a quantum whisper that travels faster than light yet carries no information that could violate causality. This might seem to contradict Einstein's special relativity, which says nothing can travel faster than light. But entanglement doesn't actually violate relativity, because no information is transmitted. The correlation is only visible when you compare measurements from both locations. From Earth alone, the moon's behavior looks random. Only when you receive a message from Mars, traveling at light speed or slower, telling you what they measured, do you see the correlation. It's like having two coins that always land on opposite faces when flipped, but you can't use them to send messages because you can't control which face your coin will show. But let's think about what this entanglement would mean for the inhabitants of our imagined universe. First, there would be the sheer wonder of it. Imagine knowing that your moon is intimately connected to another moon, orbiting a distant planet, that every measurement you make here affects something there, that the universe has threaded invisible connections between celestial bodies like a cosmic network of quantum relationships. Children would grow up learning about their sister moon around Mars, would wave at it through telescopes, knowing that in some quantum sense it's waving back. Scientists in this universe would map these entanglement networks, tracing the connections between moons, planets, even stars. They might discover that the entire solar system is entangled, that every celestial body is quantum correlated with every other in complex patterns that evolved over billions of years. There might be entanglement clusters, groups of moons that are strongly correlated with each other, and entanglement deserts, regions of space where quantum correlations are weak or absent. The night sky would be not just a collection of independent objects but a vast quantum web, each node connected to others through invisible threads of correlation. Navigation would take on new dimensions in such a universe. Spacecraft travelling between planets could use entangled moons as quantum beacons, measuring one to instantly know the state of another. While this wouldn't allow faster-than-light communication, you still couldn't send messages. It would provide a kind of quantum GPS, a way of maintaining connection with home no matter how far you travelled. Astronauts on long voyages might find comfort in knowing that their ship's quantum beacon is entangled with Earth's moon, that every measurement they make creates an instant correlation with home, a quantum heartbeat that transcends distance. The cultural implications would be profound. If celestial bodies are visibly entangled, if you can see with your own eyes that distant objects are mysteriously connected, it would shape philosophy, religion, and art in fundamental ways. The idea that everything is connected, that the universe is one interconnected whole, wouldn't be mystical speculation but observable fact. You could literally see the connections, watch them manifest in the correlated behaviour of entangled moons. Religions might develop around these quantum connections, seeing them as evidence of cosmic consciousness or divine design. Meditation practices might involve contemplating entanglement, trying to sense the invisible threads that connect all things. Artists might create works that explore entanglement themes, sculptures that change based on measurements of distant entangled objects, paintings that capture the moment of correlation when one moon's measurement affects another. But entanglement at this scale would also raise practical challenges. If measuring one moon affects another, you'd need to coordinate observations across planets to avoid unwanted correlations. There might be international, or rather interplanetary agreements about when and how to measure entangled celestial bodies. The Mars colony agrees not to measure their moon during Earth's harvest season, when farmers need stable quantum states for optimal crop growth. Violations of these agreements might cause diplomatic incidents, accusations of quantum sabotage when unexpected measurements disrupt important observations. Let me paint you a more detailed picture of a night when entanglement becomes visible. You're at an observatory with friends, gathered to watch what astronomers have predicted will be a spectacular entanglement event. 3 moons, Earth's moon, Mars's moon, and one of Jupiter's moons, are about to undergo what's called an entanglement cascade, where measuring one will trigger correlations in the others in a complex chain reaction. The night is clear, and through the telescope you can see all 3 moons in their quantum states. Earth's moon is overhead, its familiar probability cloud glowing softly. Mars is visible as a red point of light, and with the telescope you can just make out its moon's quantum haze. Jupiter looms large in the eyepiece, its entangled moon one of 4 Galilean satellites, each in its own quantum state. At precisely 10:47 p.m, astronomers on Mars perform their measurement. You don't see it happen directly, Mars is too far away, but you see its effect immediately. Earth's moon suddenly shifts, its probability cloud condensing in one region and expanding in another. The change is dramatic, like watching a soap bubble deform in slow motion. But that's just the beginning. Because Earth's moon is also entangled with Jupiter's moon, the change in Earth's moon triggers a correlation there. Through the telescope, you watch Jupiter's moon respond, its quantum state rearranging itself in response to the earthly change. But here's where it gets really interesting. Jupiter's moon is entangled not just with Earth's moon, but with several other moons in the Jovian system. The correlation cascades through them like dominoes, each moon's quantum state shifting in response to the others. You watch in awe as the entire Jovian moon system dances in quantum correlation, their probability clouds pulsing and flowing in patterns too complex to fully comprehend. It's like watching a cosmic symphony, where the instruments are moons, and the music is made of quantum correlations. The cascade continues for several minutes, correlations propagating back and forth between the entangled moons, creating interference patterns that overlap and interact. At one point, a particularly strong correlation causes Earth's moon to briefly collapse almost to a point, becoming more definite than you've ever seen it, before spreading out again into uncertainty. The crowd at the observatory gasps in appreciation, like art lovers seeing a masterpiece revealed. As the cascade settles down, and the moons return to their normal quantum states, you're left with a profound sense of connection. You've just witnessed something that spans hundreds of millions of kilometers, a correlation that transcended space itself, a dance of entangled moons that reveal the deep quantum unity underlying apparent separation. It's one thing to know intellectually that entanglement exists. It's another to see it painted across the sky in patterns of light and probability. In this universe, entanglement wouldn't just be a scientific curiosity but a practical resource. Engineers might design quantum machines that use entangled moons as components, their states providing the quantum correlations needed for computation or communication. While you couldn't send messages faster than light, the no communication theorem still holds. You could use entanglement for perfect encryption, for random number generation, for quantum computing on a cosmic scale. Imagine a quantum computer where the qubits are moons, their entangled states representing the superposition of calculations. The computer wouldn't be a box on a desk, but the entire solar system, with astronomers as programmers, measurements as operations, and the night sky as the display. Solving a problem would involve carefully orchestrated observations of different moons, their entangled correlations propagating the calculation through space. The answer would appear as a pattern in the quantum states, readable by those who knew how to interpret the cosmic quantum dance. Agriculture in this universe might depend on entanglement in unexpected ways. Farmers might plant crops according to the quantum states of entangled moons, knowing that certain correlations lead to better growth. Plant wheat when the Earth-Mars moon. Entanglement is strong, but wait for weak entanglement to plant corn. The mechanisms might be unclear. Perhaps plants are sensitive to the quantum fields, perhaps the correlations affect weather patterns, but the empirical knowledge would accumulate over generations. Weather itself might be influenced by celestial entanglement. If the atmosphere is sensitive to quantum fields, then correlations between entangled moons might trigger atmospheric changes. A measurement on Mars might instantly affect Earth's weather through the entangled moon connection, not through any physical force but through the subtle influence of quantum correlation on chaotic atmospheric systems. Weather forecasters would need to track not just pressure systems and temperatures, but also the quantum states of entangled celestial bodies and the measurement schedules of other planets. Animals in this universe would have evolved to sense and perhaps use entanglement. Migrating birds might navigate not just by magnetic fields, but by sensing the entanglement patterns between celestial bodies. Whales might sing in patterns that correlate with entangled moon states, their songs spreading through the ocean in quantum harmony with the cosmos. Some creatures might even be able to create entanglement, perhaps through bioluminescent displays bright enough to constitute measurements, allowing them to influence the quantum correlations of the night sky. There might be quantum ecology, with entanglement networks forming between living things and celestial bodies. A forest might become entangled with a moon through millions of tiny correlations built up over centuries. Cutting down the forest wouldn't just destroy habitat, but would sever quantum connections that stretch into space. Conservation would take on cosmic dimensions, protecting not just local ecosystems but the quantum entanglement networks that connect Earth to the heavens. Human relationships in such a universe might be understood through the lens of entanglement. When people say they feel connected to someone far away, they might mean it literally. Perhaps humans can become quantum entangled through shared experiences, their quantum states becoming correlated in ways that persist across distance. Love might be understood as a form of entanglement, two people's quantum states becoming so correlated that measuring one affects the other, not through any mystical force but through the same quantum mechanics that connects moons across space. This isn't to say that consciousness is quantum, that's still debated in our world, but in a universe where quantum effects are visible at large scales, it would be natural to think about human connections in quantum terms. Therapists might work with entanglement patterns, helping people understand and modify their quantum correlations with others. Relationships might be described in terms of entanglement strength, coherence time, and correlation patterns. We were strongly entangled for years, but decoherence set in, and now we're barely correlated. Art in this universe would explore entanglement in countless ways. Musicians might compose pieces for entangled instruments, where playing one automatically affects the others through quantum correlation. The instruments might be on different continents or even different planets, yet they would play in perfect correlation, creating music that literally transcends space. Dancers might perform entangled dances, their movements correlated through quantum connections, each dancer instantly responding to the others regardless of distance. Visual artists might create entangled paintings, where the quantum states of pigments on one canvas are correlated with those on another. Change one painting, perhaps by observing it in a particular way, and the other instantly changes too. Gallery visitors might influence artworks on the other side of the world just by looking at their entangled partners. Art openings might be synchronized across planets, with entangled artworks creating a shared aesthetic experience that spans the solar system. Literature too would be shaped by visible entanglement. Stories might explore the philosophical implications of correlation without causation, the mystery of connections that transcend space and time. Poetry might try to capture the feeling of being entangled, of being part of a quantum whole that extends beyond the boundaries of the self. Science fiction, or would it be science fact, might imagine civilizations that communicate through entanglement networks, that build societies based on quantum correlation rather than physical proximity. But perhaps the most profound impact would be on our understanding of identity and individuality. In a universe where entanglement is visible, where you can see that things are connected in ways that transcend space, the illusion of separation becomes harder to maintain. You might look at an entangled moon and recognize that you too are entangled, that your particles are correlated with particles throughout the universe, that the boundary between self and cosmos is more fluid than you imagined. This isn't New Age mysticism, but hard physics made visible. Every particle in your body was once in a star, and many retain quantum correlations from those stellar origins. You are literally entangled with the universe, your quantum state connected to quantum states throughout space and time. In our world, this entanglement is hidden at microscopic scales, but in our imagined universe it would be as visible as the moon in the sky, as undeniable as the tides. As we near the end of our exploration of cosmic entanglement, I want to return to the image of those two entangled moons, one orbiting Earth, the other orbiting Mars. They're separated by hundreds of millions of kilometers of empty space, yet they're more intimately connected than objects touching each other. When one is measured, the other instantly responds, not through any force or signal, but through the pure correlation that is entanglement. This is the universe telling us that space is not what we thought it was, that distance is not the barrier we imagined, that connections can transcend the physical and manifest in the quantum realm in ways that our everyday experience doesn't prepare us for. Entanglement shows us that the universe is not a collection of separate objects interacting through forces, but a single quantum system, artificially divided by our perception into distinct things, but fundamentally unified at the quantum level. And here's the beautiful truth. This isn't just true in our imagined universe of moon-sized quantum particles. It's true in our real universe too. Right now, particles in your body are entangled with particles throughout the cosmos. The photons entering your eyes from your screen are entangled with photons elsewhere. The electrons in your brain, creating the thoughts you're thinking right now, are part of vast entanglement networks that stretch across space and time. We don't see these entanglements because they're hidden at microscopic scales, and because decoherence quickly destroys quantum correlations in warm, noisy environments like our bodies. But they're there, underlying everything, connecting everything, making the universe not a collection of things but a single, vast, quantum whole. Our imagined universe of entangled moons is just making visible what's already true. We live in an entangled cosmos, where everything is connected to everything else through quantum correlations that transcend space and time. There's a moment, perhaps you've experienced it, when you're looking at something, really looking, with full attention, and it seems to change under your gaze. Maybe it's a painting in a gallery that reveals new details the longer you study it, or a loved one's face that becomes more beautiful the more carefully you observe it, or even just a simple object like a coffee cup that somehow becomes profound when you give it your complete attention. This experience, this sense that observation itself changes what we see, is usually dismissed as subjective, as something happening in our minds rather than in the world. But quantum mechanics tells us something remarkable. At the fundamental level of reality, observation really does change what's being observed. The act of measurement doesn't just reveal pre-existing properties, but actually causes them to come into being. Tonight, in our universe of moon-sized quantum particles, we're going to explore what this means when the act of observation involves not microscopic particles, but massive celestial bodies hanging in our sky. The measurement problem, as physicists call it, is perhaps the deepest mystery in quantum mechanics. Before measurement, a quantum system exists in superposition, all possibilities coexisting in a blur of probability. But when we measure it, when we ask it a definite question like, "Where are you?" or "How fast are you moving?" the superposition collapses to a single answer. The system goes from being many things at once to being just one thing, from possibility to actuality, from quantum to classical. But what exactly constitutes a measurement? What's special about observation that causes this dramatic transformation? After a century of quantum mechanics, we still don't have a complete answer. In laboratories, scientists use sophisticated instruments to measure quantum particles, photomultipliers to detect photons, cloud chambers to track particle paths, superconducting quantum interference devices to measure tiny magnetic fields. These instruments amplify quantum effects to classical scales where we can observe them. But fundamentally, a measurement happens whenever a quantum system interacts with a larger system in a way that creates a permanent record, when information about the quantum state leaks into the environment in a way that can't be undone. Now imagine this process scaled up to our moon-sized quantum particles. The moon hangs in the sky in superposition, existing in multiple places at once, its probability cloud spread across the heavens. You look up at it with your naked eyes, and photons from the moon enter your pupils, strike your retinas, trigger cascades of neural activity in your visual cortex. Is this enough to constitute a measurement? Does your casual glance collapse the moon's wave function from superposition to a definite position? In our imagined universe, let's say that the answer depends on the quality and intensity of the observation. A casual glance might cause only a partial collapse, nudging the moon's wave function toward definiteness, but not completely destroying the superposition. The moon would shimmer and fluctuate under your gaze, its quantum state responding to your attention but not fully surrendering its uncertainty. It would be like trying to hold smoke. The harder you look, the more it shifts and changes, never quite becoming solid. But if you were to observe more carefully, perhaps with a telescope, perhaps with instruments that record the moon's position precisely, the collapse would be more complete. The multiple translucent moons would converge into one, the probability cloud would condense to a point, and for as long as you maintained your observation, the moon would have a definite position in the sky. It would be as if your attention was a gentle hand, pressing the moon's quantum uncertainty into classical definiteness, holding it in place through the sheer act of observation. This would make astronomy a profoundly different endeavour in our imagined universe. Astronomers wouldn't be passive observers, but active participants in shaping celestial reality. Every measurement would be a choice, collapsing quantum possibilities into classical actualities. There would be heated debates about the ethics of observation. Should we force celestial bodies into definite states, or should we let them exist in their natural quantum uncertainty? Some might argue for minimal observation, preserving the quantum beauty of the cosmos. Others might push for comprehensive measurement, trying to map the classical skeleton beneath the quantum flesh. Imagine an observatory on a mountaintop in this universe. The astronomers arrive at sunset preparing for a night of observation. But their preparation isn't just about aligning telescopes and calibrating instruments. They must also decide what to measure and what to leave unmeasured, what to collapse and what to preserve in superposition. They might have quotas, only 3 full collapses per night. The rest must be partial observations that preserve some quantum uncertainty. They might coordinate with observatories around the world, ensuring that someone, somewhere, is always leaving each celestial body partially unmeasured, preventing the entire sky from collapsing into classical definiteness. The experience of looking through a telescope would be extraordinary. As you bring the moon into focus, you would literally see the wave function collapse. The fuzzy probability cloud would sharpen and condense, multiple positions would converge into one, the quantum moon would become classical under your gaze. It would happen smoothly but quickly, like watching time-lapse footage of clouds forming or dissolving. And the moment you looked away, the moment you stopped actively observing, the moon would begin to spread out again, returning to its quantum state like a held breath finally released. This raises profound questions about the nature of reality in such a universe. Does the moon have a definite position when no one is looking at it? The quantum mechanical answer is no. Unobserved, it exists only as a probability distribution, a tendency to be found in certain places if measured. But this seems to conflict with our intuition that the moon is really there, somewhere specific, whether we're looking or not. In our imagined universe, this wouldn't be a philosophical debate but an empirical fact. You could test it by looking away and then quickly looking back, seeing the moon spread out into uncertainty and then collapse again into definiteness. Children in this universe would play games with observation and measurement, Quantum hide-and-seek might involve trying to observe players just enough to know roughly where they are, but not enough to fully collapse their wave functions. Measurement tag might require touching someone with enough observational intensity to collapse their quantum state. These games would teach intuitive understanding of quantum mechanics, the way our games teach intuitive understanding of classical mechanics. Through play, through embodied experience, through the joy of discovery. But measurement in our imagined universe wouldn't just be about position. You could measure different properties of the quantum moon, and depending on what you chose to measure, you'd get different results. This is a consequence of the uncertainty principle, which says that certain pairs of properties, like position and momentum, or energy and time, can't be simultaneously known with perfect precision. The more accurately you measure one, the less accurately you can know the other. So imagine you're at your telescope and you have a choice. You can measure the moon's position precisely, collapsing its wave function to a definite location, but making its momentum completely uncertain. Or you can measure its momentum precisely, determining exactly how fast and in what direction it's moving, but making its position spread out into a vast probability cloud. Or you can make a compromise measurement, getting moderate information about both position and momentum, but perfect information about neither. This choice would have practical consequences. If you need to know where the moon will be for navigation, you'd measure position. If you need to predict tides based on the moon's orbital motion, you'd measure momentum. But you could never have both pieces of information simultaneously with perfect precision. The universe would force you to choose, to decide what aspect of reality you want to make definite at the cost of making other aspects uncertain. Different cultures in this universe might have different measurement philosophies. Some might prefer position measurements, valuing knowledge of where things are over how they're moving. Their night sky would show celestial bodies with definite positions but uncertain motions, creating a kind of static cosmic tableau. Others might prefer momentum measurements, valuing knowledge of cosmic dynamics over static positions. Their sky would be full of motion, with celestial bodies smeared out along their trajectories but moving with precise, known velocities. There might even be measurement artists, people who choreograph observations to create beautiful patterns in the sky. They might coordinate teams of observers around the world, having them measure different properties of different celestial bodies in carefully timed sequences. The result would be a kind of cosmic performance art, with quantum moons collapsing and spreading, their properties flickering between definite and uncertain, in patterns that tell stories or express emotions or simply create beauty for its own sake. The technology of measurement would be highly advanced in such a universe. Beyond simple telescopes, there might be quantum observation devices that can perform measurements without fully collapsing wave functions, extracting partial information while preserving some superposition. There might be entanglement-based measurements that use correlations between particles to infer properties without direct observation. There might even be measurement shields that prevent observations, preserving quantum states in regions of space where people want to maintain uncertainty. Consider what weather forecasting would be like. Meteorologists would need to decide not just what to measure, but whether to measure at all. Every observation of atmospheric quantum states would change those states, potentially altering the weather itself. There might be measurement storms caused by too many observations in one area, collapsing atmospheric wave functions in ways that trigger precipitation or wind. Weather services might have to ration measurements, carefully choosing when and where to observe to get needed information while minimizing disruption to natural weather patterns. Wildlife would have evolved various strategies for dealing with measurement and observation. Some creatures might be measurement sensitive, able to detect when they're being observed and respond by changing their behavior or even their quantum states. Prey animals might evolve quantum camouflage, spreading their wave functions out to become harder to observe precisely. Predators might develop intense observational abilities, able to collapse prey wave functions through focused attention. There might be quantum ecosystems where the act of observation plays a crucial ecological role. Imagine a forest where the trees exist in superposition during the night. Their branches and leaves spread out in probability clouds to maximize photon capture from the quantum moon. At dawn, as animals begin to observe them, the trees collapse into definite positions, their branches becoming solid enough to support nests and climbers. The daily cycle of observation and non-observation would create a rhythm of quantum and classical states that all life in the forest would adapt to, Human society would need to develop laws and customs around observation. There might be observation rights, who is allowed to measure what and when. Collapsing someone else's property without permission might be illegal. There might be quantum privacy laws protecting people's right to exist in superposition without unwanted observation. Courts might have to adjudicate disputes about measurement. Your observation of your moon interfered with my observation of my satellite, causing economic damages. Religious and philosophical systems would grapple with the implications of observation-dependent reality. Some might see consciousness as fundamental, with observation being the way consciousness shapes reality. Others might take a more materialist view, seeing measurement as just another physical interaction with no special status. There might be contemplative practices focused on learning to observe without measuring, to see without collapsing, to be aware without forcing definition. In education, teaching about measurement would be central to the curriculum. Children would learn not just what measurement is, but how to do it responsibly. There might be measurement ethics classes discussing when it's appropriate to collapse wave functions and when things should be left in superposition. Science classes would include practical exercises in partial measurement, teaching students how to extract just enough information for their needs while preserving quantum uncertainty. The arts would explore measurement in countless ways. Theatre might include audience participation where viewers' observations affect the performance, with actors existing in superposition until observed, their characters and actions becoming definite only when the audience looks at them. Literature might experiment with quantum narratives that exist in superposition until read, with each reader's observation collapsing the story into a slightly different form. Photography would be especially interesting. Every photograph would be a record of collapse, showing the moment when the photographer's observation forced the quantum world into classical definiteness. Long exposure photographs might show the evolution of collapse, the gradual transition from quantum to classical, as observation accumulates. There might be quantum photography that somehow captures superposition itself, showing the world as it exists when unobserved. Music in this universe might explore the temporal aspects of measurement. Since energy and time are complementary variables like position and momentum, measuring when something happens precisely makes its energy uncertain, and vice versa. Musicians might play with this, creating compositions where the timing is precise but the pitch is uncertain, or where the pitch is exact but the timing is quantum fuzzy. Concerts might involve real-time choices about what to measure, with the music changing based on the observations made. Let me paint you a specific scene to illustrate the poetry of measurement in this universe. You're walking along a beach at night. The quantum moon is in full superposition above you, its light creating shifting patterns on the water. The waves themselves are partially quantum, their positions not quite definite until they break on the shore, where the collision with the sand constitutes a measurement that collapses them into classical definiteness. You have a choice. You can walk with your eyes downcast, observing the sand and shells, collapsing them into definite positions beneath your feet. Or you can look up at the moon, your observation causing it to shimmer and condense, pulling it toward classical definiteness. Or you can try to observe nothing directly, keeping your gaze soft and unfocused, letting the world remain in its quantum state around you. You choose the third option, and something magical happens. Without direct observation to collapse them, the boundaries between things become fluid. The moon's light, the ocean's waves, the sand beneath your feet, even your own body, all exist in gentle superposition, their edges blurring and blending. You're not separate from the quantum beach, but part of it. Your wave function overlapping with the wave functions around you. You can feel the probability currents, the quantum tides that flow through everything. Then you hear someone calling your name. Instinctively you turn and look, and the act of focused observation collapses the quantum dream. The person becomes definite, solid, classical. The spell is broken, but the memory remains. The memory of existing in superposition, of being part of the quantum whole rather than a classical observer separate from it. This experience would be available to everyone in our imagined universe. This ability to choose between quantum and classical experience through the simple act of observation or non-observation. It would add a layer of richness to existence that we can barely imagine, a constant dance between definition and uncertainty, between knowing and not knowing, between the classical world of everyday experience and the quantum realm of pure possibility. Scientists in this universe would study the mechanism of collapse intensively. What exactly happens when observation causes superposition to become definite? Is it instantaneous, or does it take time? Does it propagate at a finite speed or happen everywhere at once? These questions, which in our world are mostly theoretical, would have practical implications in a universe where collapse is visible and affects moon-sized objects. There might be different interpretations of quantum mechanics, just as in our world, but they would be testable with cosmic-scale experiments. The Copenhagen interpretation would say that observation causes real collapse. The many-worlds interpretation would say that observation causes the universe to branch, with different versions of you seeing different outcomes. The pilot wave theory would say that particles always have definite positions and observation just reveals them. Each interpretation would make different predictions about what you'd see when observing quantum moons, and experiments could potentially determine which is correct. The philosophy of mind would be deeply intertwined with physics in such a universe. If conscious observation can collapse moon-sized wave functions, what does that say about consciousness itself? Is consciousness fundamental to physics, or is it just another physical process that happens to cause measurement? Do all conscious beings collapse wave functions equally, or do some have more measurement power than others? Do unconscious devices cause collapse, or is awareness necessary? These wouldn't be abstract philosophical questions, but practical concerns with observable consequences. You might be able to test whether a sleeping person's unconscious observation causes collapse, whether animals cause the same kind of collapse as humans, whether artificial intelligences can measure quantum systems. The results would have profound implications for how the inhabitants of this universe understand themselves and their place in the cosmic order. As we near the end of our exploration of measurement and observation, I want to emphasize how this aspect of our imagined universe reveals something profound about our real universe. The measurement problem isn't just a quirk of quantum mechanics, it's telling us something deep about the nature of reality and our role in it. Even in our world, where quantum effects are hidden at microscopic scales, every observation is changing what's observed, every measurement is selecting one possibility from many, every conscious moment is participating in the creation of classical reality from quantum possibility. The moon-sized quantum particles we've been imagining are just a way of making visible what's already happening all around us, all the time, at scales too small to see. Every photon that enters your eye, every particle that interacts with your body, every quantum system that becomes entangled with your brain. All of these involve measurement, observation, the collapse of possibility into actuality. You're not just observing reality, you are participating in its creation, one measurement at a time. Let us zoom out now, far beyond the Earth and its quantum moon, beyond the solar system with its entangled satellites, out to the vast scales where galaxies spin in the darkness and the universe reveals its largest structures. In our real cosmos, these immense formations, spiral galaxies, elliptical galaxies, galaxy clusters, and the cosmic web itself, are governed primarily by gravity, that most familiar and yet most mysterious of forces. But in our imagined universe where quantum effects persist at astronomical scales, where moons exist in superposition and planets can be entangled, how would gravity behave? How would galaxies form? What would the large-scale structure of the universe look like when quantum mechanics and general relativity must work together, not just in the extreme conditions of black holes, but everywhere, all the time, at every scale? This is perhaps the most profound aspect of our thought experiment, because in our real universe, physicists have been struggling for decades to unite quantum mechanics and general relativity into a single theory of quantum gravity. The two theories, both incredibly successful in their own domains, seem fundamentally incompatible. General relativity describes gravity as the curvature of space-time, a smooth, continuous geometry that massive objects create and through which all things move. Quantum mechanics describes a universe of discrete particles and probabilistic events, where uncertainty is fundamental and observation plays a special role. At the Planck scale, 10⁻⁵ meters, these two descriptions collide and we don't yet know what happens. But in our imagined universe, we don't need to solve quantum gravity mathematically. We can simply imagine what we might see if quantum effects scaled up to astronomical sizes, if gravity had to deal not with point masses, but with probability clouds the size of moons and planets. The result would be a cosmos, unlike anything we know, where the very fabric of space-time would ripple with quantum uncertainty, where mass itself would be indefinite until measured, where the graceful dance of celestial mechanics would be replaced by a quantum choreography of probability and correlation. Let's start with a single quantum planet orbiting a quantum star. In our classical universe, the planet follows an elliptical orbit determined by the balance between its momentum and the star's gravitational pull. The orbit is predictable, stable, repeating with clockwork precision. But if both the star and planet are quantum objects, existing in superposition, having indefinite positions until measured, how would gravity work between them? One possibility is that gravity would respond to the entire probability distribution of mass, not just to definite point masses. The planet's wave function would evolve under the influence of the star's probability cloud, and vice versa. Instead of a simple elliptical orbit, you'd have a quantum orbital, a probability distribution that shows where the planet is likely to be found if measured. This orbital wouldn't be static, but would evolve over time, breathing and shifting as the wave functions of planet and star interact. The result might look like a cosmic aurora, with the planet's probability cloud forming shells and bands around the star, denser in some regions, thinner in others, with interference patterns where different parts of the wave function overlap. The orbit would be more like a standing wave, a stable pattern in the probability field that persists over time but never quite repeats exactly. Sometimes the planet's wave function might tunnel through barriers, appearing on the opposite side of its orbit without passing through the space between. Other times it might exist in superposition, orbiting in multiple places simultaneously until observation collapses it to a single path. Now scale this up to an entire galaxy. In our universe, galaxies are vast collections of stars, gas, dust, and dark matter, all held together by gravity in a delicate balance between rotation and gravitational collapse. The spiral arms of galaxies like our Milky Way are density waves, regions where stars and gas are temporarily more concentrated as they orbit the galactic center. But in a quantum universe, these structures would be far more exotic. Imagine a galaxy where every star is a quantum object, its position uncertain, its mass indefinite until measured. The galaxy wouldn't have sharp spiral arms, but rather probability flows, streams of stellar likelihood that wind around the galactic center in quantum spirals. Where probability streams cross, you'd see interference patterns, bright regions where constructive interference makes stars more likely, dark regions where destructive interference creates probability voids. The galactic center, where in our universe we find supermassive black holes, would be even stranger in a quantum cosmos. A quantum black hole wouldn't have a definite event horizon, but rather a probability gradient, a region where the likelihood of escape decreases smoothly rather than dropping to zero at a sharp boundary. Matter falling into such a black hole wouldn't simply disappear beyond the event horizon, but would enter a superposition of fallen and not fallen states, creating a halo of probability around the black hole where things exist in quantum limbo between capture and escape. Dark matter, that mysterious substance that makes up most of the mass in our universe but doesn't interact with light, might be easier to understand in a quantum universe. Perhaps dark matter is simply ordinary matter that exists in a different quantum state, out of phase with the matter we can see. In our imagined universe, you might be able to shift between states, seeing sometimes the ordinary matter galaxy, sometimes the dark matter galaxy, both occupying the same space but in different quantum configurations. The formation of such galaxies would be a process unlike anything in our classical universe. In our cosmos, galaxies formed from tiny density fluctuations in the early universe, regions where matter was slightly more concentrated that grew over billions of years through gravitational attraction. But in a quantum universe, galaxy formation might proceed through quantum phase transitions, sudden shifts where vast regions of space simultaneously change their quantum state, like water suddenly freezing into ice. You might witness such a transition, a vast cloud of quantum gas, existing in superposition across millions of light years, suddenly collapsing into a more definite state as some cosmic measurement occurs. The collapse wouldn't happen from outside in or inside out, but everywhere at once, a coordinated quantum event that transforms diffuse probability into structured patterns. The resulting galaxy would bear the imprint of this quantum birth, its structure determined not just by gravity, but by the quantum correlations present at the moment of transition. The cosmic web, that vast network of galaxy clusters and filaments separated by enormous voids that defines the large-scale structure of our universe, would be even more spectacular in a quantum cosmos. The filaments wouldn't be simple chains of galaxies, but quantum probability channels, regions where the wave functions of countless galaxies overlap and interfere. The voids wouldn't be empty but would contain galaxy probability, regions where galaxies could exist but are unlikely to be found when measured. Travel through such a universe would be extraordinary. As your spacecraft moves through space, it would encounter probability gradients, regions where the likelihood of finding matter increases or decreases. You might enter a probability void where stars and planets are unlikely, where space itself seems thinner, less definite. Then you'd emerge into a probability peak, a region where matter is highly likely, where every measurement reveals new stars, new planets, new wonders. Navigation would require quantum maps, charts that show not where things are but where they're likely to be. There's a 70% probability of finding a star system in this region, with quantum fluctuations of plus 10 light-years. Explorers would need to be comfortable with uncertainty, ready to find either rich stellar neighborhoods or vast emptiness, depending on how the wave functions collapse when observed. The evolution of the universe itself would be different. In our cosmos, the universe is expanding, with galaxies moving apart as space itself stretches. Dark energy, a mysterious force that accelerates this expansion, makes up about 70% of the energy density of the universe. But in a quantum universe, expansion might be a quantum phenomenon, with space itself existing in superposition of different sizes until measured. The universe might breathe, expanding and contracting in quantum superposition, only becoming definite when observed on the larger scales. Dark energy might be the energy of the quantum vacuum, the endless fluctuations of virtual particles that fill even empty space. The fate of the universe, whether it will expand forever, collapse in a big crunch, or reach some stable size, might not be determined but might exist in superposition until some final cosmic measurement forces a choice. Life in such a universe would have evolved to work with these quantum gravitational effects. Civilizations might build their cities in probability peaks, regions where matter is most likely to remain stable. They might use quantum tunneling for transportation, adjusting their wave functions to increase the probability of being where they want to go. They might harness the energy of quantum gravitational fluctuations, extracting power from the uncertainty of space-time itself. Imagine a civilization that has learned to manipulate gravity quantumly. They might create gravitational standing waves, stable patterns in space-time that provide artificial gravity without mass. They might build structures that exist in gravitational superposition, experiencing multiple gravitational fields simultaneously until observed. They might even create gravitational entanglement, linking distant regions of space through quantum correlations in the gravitational field. Their architecture would be unlike anything we can imagine. Buildings might be probability structures, existing in superposition of different configurations until observed. Cities might be quantum patterns, stable wave functions in the gravitational field that provide shelter and structure without solid matter. Transportation networks might use gravitational quantum tunneling, allowing instant travel between probability peaks without crossing the space between. The science of such a civilization would be far advanced beyond ours, but also fundamentally different. They wouldn't see quantum mechanics and general relativity as separate theories to be unified, but as aspects of a single quantum gravitational reality that they experience every day. Their physics would be intuitive in ways ours cannot be, based on direct observation of quantum gravitational effects rather than mathematical extrapolation from limited experiments. They might discover things we can only dream of, ways to create and destroy matter through quantum gravitational effects, methods for travelling faster than light using quantum tunneling on cosmic scales, techniques for communicating across the universe through gravitational entanglement. Or they might discover fundamental limitations we haven't imagined, quantum gravitational principles that constrain what's possible in ways our separate theories of quantum mechanics and general relativity don't reveal. Let me paint you a picture of what it might be like to witness the universe at these scales. You're in a spacecraft equipped with quantum sensors, travelling through intergalactic space. Outside your window, the cosmos doesn't look like the star-filled darkness we know, but more like an ocean of probability, with waves and currents of likelihood flowing through space. Ahead, you see a galaxy, but not as a distinct collection of stars. Instead, it appears as a vast probability storm, a region where stellar wave functions concentrate and interfere. The spiral arms are not solid structures but standing waves in the probability field, patterns that persist even as individual star wave functions flow through them. The galactic center glows with quantum uncertainty, a bright haze where probability density is highest and quantum effects are strongest. As you approach, you begin to feel the galaxy's gravitational field, but it's not the smooth, predictable force you expect. Instead, it fluctuates and pulses, responding to the quantum state of the galaxy's mass distribution. Sometimes you're pulled strongly toward the center, other times the pull weakens as the galaxy's mass exists in superposition farther from your position. Your trajectory becomes uncertain, a probability path rather than a definite course. You decide to make an observation, to measure the position of nearby stars precisely. As you do, something remarkable happens. The fuzzy probability storm begins to condense, stars crystallizing out of the uncertainty like frost forming on glass. The gravitational field becomes more definite, your trajectory more certain. But you know this is temporary. As soon as you stop observing, the galaxy will return to its quantum state, spreading out again into beautiful uncertainty. You pass through the galaxy, experiencing regions of high and low probability, places where stars are likely and unlikely. In the probability peaks, space feels thick with possibility, pregnant with unobserved stars waiting to be discovered. In the probability voids, space feels thin, attenuated, as if reality itself is less concentrated here. You realize that in this universe, emptiness and fullness are not binary states but continuous gradients of likelihood. Emerging on the other side of the galaxy, you look back and see it as a whole, a vast quantum system, billions of stars in correlated superposition, their wave functions entangled through gravity and light, the entire structure breathing with quantum life. It's beautiful beyond words, this cosmic quantum symphony, this gravitational dance of probability and possibility. The implications for cosmology in such a universe would be profound. The Big Bang might not have been a classical explosion but a quantum event, the universe beginning in superposition of many possible states and only gradually collapsing toward the classical through observation and decoherence. The cosmic microwave background radiation, that faint echo of the Big Bang that fills our universe, might show quantum interference patterns, the fossilized remnants of the universe's quantum birth. Inflation, that period of rapid expansion in the early universe, might be understood as a quantum phase transition, a sudden change in the universe's quantum state that drove exponential growth. The formation of the first stars and galaxies might have proceeded through quantum nucleation, with stellar wave functions condensing out of the primordial gas like quantum droplets in a cosmic cloud chamber. Even the fundamental constants of nature, the speed of light, the gravitational constant, the fine structure constant, might not be truly constant in a quantum universe. They might exist in superposition, having slightly different values in different regions of space or at different times, only becoming definite when measured precisely. This would add another layer of uncertainty to the universe, a fundamental indefiniteness that goes beyond the position and momentum of particles to the very laws of physics themselves. The anthropic principle, the observation that the universe seems fine-tuned for life, might have a quantum explanation in such a cosmos. Perhaps life itself acts as a cosmic measurement device, collapsing the universal wave function towards states that support observers. The universe might exist in superposition of many possible configurations until life evolves to observe it, at which point it collapses toward life-friendly parameters. We wouldn't be lucky to live in a universe that supports life. Rather, our observation would partially determine the universe's properties. As we contemplate these cosmic scales, where quantum mechanics and gravity intertwine to create a universe of unprecedented beauty and strangeness, we're reminded that even our real universe might be quantum at its larger scales. We know that quantum effects can persist in systems of trillions of atoms under the right conditions. We know that the universe began in a state where quantum effects were important even on cosmic scales. We know that black holes seem to require a quantum description to resolve their information paradoxes. Perhaps the universe we imagine, where quantum effects are visible at astronomical scales, is not so different from our own. Perhaps we simply haven't learned to see the quantum nature of the cosmos yet, haven't developed the tools or perspectives necessary to perceive the probability waves that might underlie even the largest structures. Our thought experiment might be less imagination than anticipation, a preview of what we'll discover as our understanding of quantum gravity develops. The gentle truth is that the universe is quantum all the way down and all the way up. The classical world we experience with its definite positions and predictable motions is the exception rather than the rule, a special case that emerges under particular conditions but is not fundamental. By imagining quantum effects at cosmic scales, we're not creating a fantasy but exploring the deep nature of reality, seeing what the universe might be like if the quantum veil were lifted and the true, probabilistic nature of existence were revealed. As this chapter draws to a close and we prepare to explore how life and consciousness might exist in such a quantum cosmos, take a moment to appreciate the profound beauty of what we've imagined. A universe where galaxies are probability storms, where gravity responds to uncertainty, where the cosmic web is woven from quantum correlations. A universe that breathes with possibility, that exists in superposition until observed, that reveals new wonders every time we look. This is not just a thought experiment, but a meditation on the nature of reality itself, an exploration of what might be hiding just beyond the edge of our perception, waiting to be discovered. There is something deeply moving about watching life persist in the most unlikely places, a flower pushing through concrete, bacteria thriving in boiling springs, birds navigating thousands of miles through storms and darkness to return home. Life, it seems, finds a way to exist wherever existence is possible, adapting to conditions that would seem impossible, turning constraints into opportunities, transforming harsh environments into homes. Tonight, as we continue our journey through a universe where quantum particles are the size of moons, we turn our attention to perhaps the most profound question of all. How would life itself evolve and exist in such a cosmos? What would it mean to be conscious, to be alive, to experience reality in a universe where uncertainty is visible in the sky above, where the ground beneath your feet might exist in superposition, where your very atoms participate in cosmic-scale quantum dances? Let us begin by imagining a world, not Earth as we know it, but an Earth-like planet in our quantum universe, orbiting a star that exists in perpetual superposition, beneath skies filled with quantum moons, whose positions are never quite definite until observed. The sun, if we can call it that, doesn't rise from a specific point on the horizon, but rather brightens gradually from a probability distribution, the eastern sky growing luminous with quantum dawn as the star's wave function evolves toward morning configurations. The light that reaches the planet's surface isn't steady but flickers with quantum uncertainty, its intensity and wavelength fluctuating as the star exists in superposition of different fusion states. On this world, evolution would have taken a very different path. The first primitive life forms, perhaps something like our bacteria, would have emerged in an environment where quantum effects dominate not just at molecular scales, but at scales visible to what would eventually become eyes. These early organisms wouldn't just need to manage chemical reactions and energy gradients. They would need to navigate probability currents, survive in superposition, extract energy from uncertain light, and reproduce in a world where even their own existence might be indefinite until observed. Consider photosynthesis in such a world. On Earth, plants capture photons from the sun and use their energy to convert carbon dioxide and water into sugars. It's a quantum process even in our world. Researchers have discovered that quantum coherence plays a crucial role in the efficiency of photosynthesis, allowing energy to explore multiple pathways simultaneously and find the most efficient route to the reaction center. But in our imagined universe, where the sun itself is quantum and its light arrives in superposition, photosynthesis would be even more exotic. Plants might evolve leaves that can exist in superposition, spreading their quantum wave functions to match the uncertain sunlight. When the sun is broadly distributed in probability space, the leaves would spread out too, becoming translucent, almost ghostly, maximizing their overlap with the star's uncertain position. When the sun becomes more definite, perhaps when observed by other organisms or measurement devices, the leaves would condense, becoming more solid, more classically plant-like. You might walk through a forest that breathes with quantum uncertainty, the trees shifting between definite and indefinite states as the day progresses. The chlorophyll-like molecules in these plants wouldn't just absorb single photons, but entire probability distributions of light. They might use quantum interference to separate different wavelengths, creating internal interference patterns that concentrate energy at reaction centers. The plants might even be able to influence the sun's wave function through their collective observation, millions of leaves acting as a distributed measurement device that partially collapses the star towards states that provide optimal light for photosynthesis. Animals in this universe would face unique challenges and opportunities. How do you hunt prey that might exist in superposition? How do you flee from predators that could be in multiple places at once? How do you navigate when landmarks themselves are quantum objects with uncertain positions? Evolution would have found answers to these questions, creating organisms unlike anything in our classical world. Imagine a predator that hunts using quantum observation. It has evolved eyes that can perform weak measurements, observations that extract some information about prey location without fully collapsing the prey's wave function. The predator stalks its target in probability space, gradually narrowing down the prey's likely positions through repeated weak measurements. When the probability distribution is sufficiently concentrated, the predator makes a strong measurement, a focused observation that collapses the prey to a definite location and then strikes. The prey, in turn, might have evolved quantum camouflage. When it senses it's being observed, perhaps through quantum backaction, the subtle effect that measurement has on the measured system, it spreads its wave function out, becoming less definite, harder to pinpoint. It might even be able to split its wave function, existing in multiple positions simultaneously, confusing predators about which component to chase. The result would be an evolutionary arms race in quantum observation and evasion, each species developing more sophisticated ways to measure and avoid measurement. Migration in such a world would be fascinating. On Earth, birds navigate using magnetic fields, star positions, and landmarks. But in our quantum universe, migrating animals might navigate using entanglement. Perhaps they become quantum entangled with their destination during their first migration, creating a correlation that persists across years and distances. When it's time to return, they don't follow a path through space, but rather adjust their quantum state to increase correlation with their destination, using entanglement as a quantum compass that points not through space, but through probability. Some creatures might migrate not through space, but through quantum states. When winter comes and food becomes scarce, instead of flying south, they might shift into a different quantum configuration, where resources are more abundant. From our perspective, they would seem to fade from one reality and emerge in another, their migration taking them not across geography, but across the quantum landscape of possibility. Communication between organisms would involve quantum channels we can barely imagine. Animals might sing not just with sound, but with quantum states, creating entangled songs where the quantum state of the singer becomes correlated with the quantum state of the listener. A bird's mating call might literally change the quantum state of potential mates, creating correlations that draw them together not through space, but through probability. Wolves might howl in quantum superposition, their voices existing in multiple tones simultaneously until heard, at which point the howl collapses to a specific pitch that conveys information about the pack's quantum state. Now let's consider how consciousness itself might work in such a universe. This brings us to one of the deepest questions in philosophy and science. What is the relationship between consciousness and quantum mechanics? In our world, this is largely speculative. Some scientists propose that consciousness might involve quantum processes in the brain, perhaps in the microtubules of neurons. Others argue that the warm, wet environment of the brain would cause any quantum states to decohere far too quickly to play a role in consciousness. But in our imagined universe, where quantum effects persist at large scales, where decoherence is suppressed or absent, consciousness would almost certainly involve quantum processes. Thoughts might exist in superposition, allowing minds to consider multiple ideas simultaneously until the moment of decision collapses them to a single choice. Memory might involve entanglement, with experiences creating quantum correlations that persist across time. Creativity might emerge from quantum tunneling, with ideas jumping across barriers in thought space that classical thinking couldn't cross. Beings in this universe might experience consciousness very differently from us. They might be aware of their own superposition, feeling themselves existing in multiple states simultaneously. Making a decision might be a visceral experience, feeling the collapse of their quantum state from many possibilities to one. They might be able to maintain certain thoughts in superposition indefinitely, holding contradictory ideas in their minds without cognitive dissonance, because the ideas genuinely coexist in quantum superposition rather than classical contradiction. These beings might develop forms of consciousness we can't imagine. Perhaps they could entangle their thoughts with others, creating collective consciousness that transcends individual minds. Perhaps they could observe their own quantum states, causing controlled collapses that allow them to choose not just what to think, but how to think. Perhaps they could maintain quantum coherence across their entire neural networks, thinking with their whole brains as single quantum systems rather than classical networks of neurons. The implications for society and culture would be profound. In a world where consciousness is obviously quantum, where thoughts can exist in superposition and minds can be entangled, the boundaries between self and other would be far more fluid. Empathy might not be just understanding another's feelings, but literally sharing their quantum state. Love might involve genuine entanglement, two consciousness becoming quantum correlated in ways that persist regardless of distance. Education in such a society would be radically different. Children would learn to maintain and collapse superposition states, to create and break entanglement, to observe without measuring. These wouldn't be abstract concepts but practical skills, as fundamental as reading and writing are to us. Mathematics might be taught through direct quantum experience, students feeling probability distributions, experiencing interference patterns, navigating complex Hilbert spaces not through equations but through consciousness itself. Art in this quantum conscious society would explore the nature of observation and experience in ways we can only dream of. Musicians might compose pieces that exist in superposition, with multiple melodies coexisting until the listener's consciousness collapses them to a specific musical experience. Each performance would be unique, shaped by the quantum states of both performers and audience. Visual artists might create works that respond to observation, changing based on who's looking and how they're looking, making each viewing a unique collaboration between artist, artwork, and observer. Writers might develop quantum narratives where stories exist in superposition, with multiple plot lines coexisting until read. The act of reading would collapse the narrative to a specific story, but different readers might collapse it differently based on their own quantum states. Books might be entangled with their readers, the story evolving based on quantum correlations between text and consciousness. Libraries would be probability spaces where all possible stories exist simultaneously, waiting for readers to collapse them into specific narratives. Philosophy and spirituality would grapple with questions that are abstract for us but concrete for them. If consciousness can exist in superposition, what does that mean for identity? Are you the same person in all branches of your superposition, or are you multiple people existing simultaneously? If minds can be entangled, where does one person end and another begin? If observation by consciousness collapses quantum states, does that make consciousness fundamental to reality, or is it just another physical process? These beings might develop spiritual practices based on quantum consciousness. Meditation might involve expanding one's wave function, spreading consciousness across probability space to experience multiple states simultaneously. Prayer might be understood as creating entanglement with the divine, whatever they conceive that to be. Enlightenment might mean achieving perfect quantum coherence, existing in pure superposition without decoherence, experiencing all possibilities simultaneously without collapse. Let me paint you a scene of daily life in this quantum conscious world. You wake, or perhaps you transition from one form of consciousness to another as the quantum dawn brightens the sky. Your thoughts, which have been in broad superposition during sleep, begin to collapse toward waking states. You don't remember your dreams so much as feel the echoes of all the possibilities your sleeping mind explored. You rise and look out your window. The city outside exists in its morning superposition, buildings slightly indefinite, their positions not quite certain until observed. Your neighbours are beginning their days too, and you can feel the subtle quantum correlations as consciousness throughout the city awakens and begins to observe, gradually collapsing the urban environment toward its daily classical configuration. You prepare breakfast, working with food that exists in probability distributions. The fruit might be ripe and unripe simultaneously until you taste it. The tea might be hot and cold in superposition until you drink it. Cooking involves not just combining ingredients, but managing their quantum states, encouraging certain probability collapses while maintaining others in superposition for texture and flavor. At work, perhaps you're what they call a quantum architect, designing buildings that exist in superposition. You collaborate with colleagues not just through words and images, but through direct quantum correlation. You entangle your thoughts with theirs, exploring design possibilities and shared superposition. Decisions emerge not through discussion, but through collective wave function collapse, the team's consciousness converging on solutions that no individual could have reached alone. In the evening, you attend what they call a probability performance, where artists create experiences in superposition. The stage exists in multiple configurations simultaneously. The performers are in superposition of different characters, different actions. As the audience observes, the performance collapses toward specific states, but never completely, always maintaining some quantum uncertainty, some possibility for surprise. Each person in the audience sees something slightly different based on how their consciousness interacts with the quantum performance. Later, walking home under the quantum moons, you reflect on the day. Your thoughts exist in superposition, satisfied and unsatisfied, happy and melancholic, excited and calm, all simultaneously true until you choose to collapse them toward a specific emotional state. But you don't have to choose. You can hold the superposition, experiencing the full spectrum of feeling without having to reduce it to a single emotion. This is life in a quantum-conscious universe, richer, more complex, more uncertain than our classical experience, but also more connected, more possibility-filled, more alive with potential. Every moment contains multiple moments. Every choice contains all choices. Every person is both themselves and part of a larger quantum whole. The children of this world would grow up with intuitions we can barely imagine. They would play games where winning and losing exist in superposition until the game ends. They would tell stories that change with each telling, not through forgetfulness, but through quantum uncertainty. They would form friendships that involve genuine quantum entanglement, feeling each other's states across distance and time. Their education would prepare them for careers we can't conceive of. Quantum farmers who manage superposition crops, probability engineers who design uncertainty into stable structures, entanglement counselors who help people manage their quantum correlations with others, observation specialists who know how to measure precisely enough to get needed information while preserving beneficial uncertainty. Science in this world wouldn't be about discovering fixed laws, but about understanding probability flows, mapping the quantum landscape, learning to navigate uncertainty. Scientists might be more like artists, working with intuition and feeling as much as logic and mathematics. Experiments wouldn't just test hypotheses, but would be creative acts, explorations of what's possible when consciousness and quantum mechanics dance together. Technology would be based on consciousness quantum interfaces, machines that respond to superposition thoughts, computers that process not just information, but uncertainty itself. Transportation that moves through probability space rather than physical space. Communication devices that use entanglement to share not just words, but actual experiences, quantum states, pieces of consciousness itself. Medicine would work with the quantum nature of life. Doctors wouldn't just treat classical symptoms, but would work with the patient's quantum state, adjusting probability distributions, managing entanglement, encouraging beneficial superpositions. Disease might be understood as decoherence, health as quantum coherence. Healing might involve not adding or removing substances, but shifting quantum states, collapsing beneficial possibilities into actuality. As we contemplate this world where life and consciousness are thoroughly quantum, we're reminded that even in our classical-seeming world, life might be more quantum than we realize. Recent research has found quantum effects in photosynthesis, in bird navigation, possibly in neural processing. The difference between our world and our imagined one might be one of degree rather than kind. We too are quantum beings, just operating in a regime where decoherence usually hides the quantum nature of our existence. Perhaps consciousness itself, even in our world, is where classical and quantum meet. Perhaps the feeling of free will, of choice, of creativity, emerges from quantum processes in our brains that we're only beginning to understand. Perhaps the hard problem of consciousness, how subjective experience emerges from objective processes, requires a quantum answer, an understanding of how observation and consciousness are related at the fundamental level. Now we must perform a gentle turn, a slow pivot from imagination back toward reality, though the boundary between the two might be less distinct than we initially thought. We've spent these hours together exploring a universe where quantum particles are the size of moons, where superposition paints the night sky, where entanglement connects distant worlds, where consciousness itself participates in the quantum dance. But this has all been a thought experiment, a journey of imagination designed to help us understand something profound about the actual universe we inhabit. The time has come to return to our real cosmos, to the world where quantum effects hide at microscopic scales, where the moon follows a predictable orbit, where the stars shine with steady light. Yet as we make this return, we'll discover that the real universe is no less mysterious, no less beautiful, no less quantum than the one we've imagined. The truth is that everything we've explored in our thought experiment, superposition, entanglement, measurement, quantum consciousness, all of it is real. It's happening right now, all around you, within you, as part of you. The only difference is scale. In our imagined universe, we expanded quantum effects to astronomical sizes so we could see them, feel them, experience them directly. In our real universe, these same effects are confined to the atomic and subatomic realm, hidden from our direct perception, but no less present, no less important, no less fundamental to the nature of reality. Let's start with superposition, that strange ability of quantum objects to exist in multiple states simultaneously. In our imagined universe, we pictured moons existing in multiple positions at once, their quantum uncertainty visible in the night sky. In our real universe, electrons in atoms exist in exactly this kind of superposition, occupying multiple orbital states simultaneously until measured. The electrons in the atoms of your body, the device you're using to hear these words, the air you're breathing, all exist in superposition, their positions and momenta uncertain, their states indefinite until interaction forces them to become specific. Scientists have demonstrated superposition with larger and larger objects over the years. They've created superposition states in molecules containing thousands of atoms. They've put tiny mechanical oscillators, visible under microscopes, into superposition of vibrating and not vibrating. They've even proposed experiments to put living organisms, viruses, tardigrades, perhaps eventually cats, into superposition. The boundary between quantum and classical isn't fixed, but depends on how well we can isolate systems from environmental decoherence. In laboratories around the world right now, scientists are pushing this boundary, creating what they call macroscopic quantum states. At MIT, researchers have created quantum superposition in objects containing trillions of atoms. In Vienna, physicists have demonstrated quantum interference with molecules containing over 25,000 protons, neutrons, and electrons. These aren't moon-sized objects, but they're far larger than the individual particles where quantum effects were first observed. Who's to say where the limit lies? Perhaps there is no limit. Perhaps under the right conditions, even moons could exist in superposition. Entanglement too is very real in our universe. Right now, photons from the sun are arriving at Earth entangled with photons that went in other directions, their quantum states correlated across millions of kilometers. Scientists have created entangled photons and sent them through kilometers of optical fiber, maintaining their correlation despite the distance. The Chinese satellite Michus has demonstrated entanglement between ground stations separated by over 1,200 kilometers, showing that quantum correlation can span continents. But entanglement isn't just a laboratory curiosity, it might be essential to life itself. Researchers have found evidence that birds use quantum entanglement in their navigation, with certain proteins in their eyes creating entangled electron pairs that are sensitive to Earth's magnetic field. The efficiency of photosynthesis seems to depend on quantum entanglement between chlorophyll molecules, allowing energy to explore multiple pathways simultaneously. Even human consciousness might involve entanglement. Some researchers propose that quantum correlations in neural microtubules could be the basis of unified conscious experience. The measurement problem we explored with our cosmic scale observations is one of the deepest mysteries in real quantum mechanics. Every time a photon hits your retina, every time a particle detector clicks, every time any quantum system interacts with a larger system in a way that creates a record, measurement occurs and superposition collapses to definiteness. But we still don't fully understand what constitutes a measurement, what role consciousness plays, why observation seems to have this special power to transform possibility into actuality. This isn't just philosophical speculation, it has practical implications. Quantum computers work by maintaining superposition and entanglement among their qubits, performing calculations on all possible states simultaneously. But measurement, even unintended measurement from environmental interaction, causes decoherence, collapsing the quantum computation to classical states. Engineers spend enormous effort isolating quantum computers from any interaction that might constitute measurement, cooling them to near absolute zero, shielding them from electromagnetic fields, suspending them to avoid vibrations. The relationship between quantum mechanics and gravity that we explored in our galactic-scale thought experiment is one of the most active areas of research in physics. We know that both theories are incredibly successful in their domains. Quantum mechanics describes the small, general relativity describes the large and massive. But when we try to combine them, when we try to understand what happens at the Planck scale, where quantum effects and gravitational effects are both important, our mathematics breaks down. String theory, loop quantum gravity, and other approaches attempt to unite these theories, suggesting that space-time itself might be quantum at the smallest scales. Some theories propose that gravity might cause wave function, collapse that the curvature of space-time by mass might be what transforms quantum superposition into classical definiteness. Others suggest that quantum mechanics might modify gravity at small scales, creating a quantum geometry that differs from Einstein's smooth space-time. Recent experiments have begun to probe this interface. Scientists have proposed putting massive objects into superposition to see how gravity behaves when mass itself is uncertain. They've suggested tests of whether gravity can be entangled, whether gravitational fields can exist in superposition. These experiments are at the very edge of our technological capabilities, but they might reveal whether the universe we imagined, where quantum effects and gravity intertwine at large scales, has any echo in reality. The quantum nature of life that we explored in our imagined world might be closer to reality than we thought. Quantum biology is a rapidly growing field, discovering quantum effects in biological systems that were thought to be too warm and noisy for quantum coherence. Beyond photosynthesis and bird navigation, researchers have found evidence of quantum effects in enzyme catalysis, DNA mutation, olfaction, and possibly even neural processing. The brain in particular might be more quantum than we've assumed. While the warm, wet environment of neurons seems hostile to quantum coherence, some researchers argue that evolution might have found ways to protect quantum states, to use quantum effects for computation and consciousness. Roger Penrose and Stuart Hameroff have proposed that consciousness emerges from quantum processes in neural microtubules. Others suggest that the brain might use quantum entanglement to bind distributed neural activity into unified conscious experience. Even if consciousness isn't fundamentally quantum, the brain certainly processes quantum information. Every photon that enters your eye is a quantum object. The rhodopsin molecules in your retina respond to single photons, amplifying quantum events to neural signals. Your visual system evolved to extract information from quantum light, to make sense of a fundamentally quantum world. In this sense, we're all quantum observers, collapsing wave functions with every glance, participating in the transformation of quantum possibility into classical experience. The technology of our real world increasingly depends on quantum effects. The computer or phone you're using contains billions of transistors that work because of quantum tunneling. GPS satellites must account for relativistic effects to maintain accuracy. MRI machines use quantum spin states to image your body. Lasers, LEDs, solar cells all depend on quantum mechanics. We live in a quantum technological civilization, even if we don't usually think of it that way. And this is just the beginning. Quantum computers are becoming more powerful each year, promising to revolutionize everything from drug discovery to cryptography. Quantum sensors can detect gravitational waves, dark matter, even single neurons firing. Quantum communication networks are being built that use entanglement for unhackable encryption. We're entering what some call the second quantum revolution, where we don't just use quantum effects but control them, engineer them, design them into our technology. Let me paint you a picture of the actual quantum world you inhabit right now. As you lie or sit there, every atom in your body is a quantum system. The electrons orbit nuclei not in definite paths, but in probability clouds, their positions uncertain until measured. The chemical bonds holding your molecules together are quantum phenomena, electron wave functions overlapping and interfering. The very stability of matter depends on quantum mechanics. Without the uncertainty principle, electrons would spiral into nuclei and atoms would collapse. The light reaching your eyes, whether from a screen or a lamp or filtered sunlight, arrives as photons, quantum particles that travelled as waves but interact as particles. Each photon carries a tiny amount of energy, its wavelength determining its colour, its quantum state determining its polarization. Some of these photons might be entangled with photons elsewhere, their quantum states correlated across space. The air you're breathing is a quantum gas, its molecules bouncing off each other in quantum collisions, their velocities distributed according to quantum statistics. The oxygen molecules that enter your lungs, bind to hemoglobin, and travel to your cells undergo quantum transitions, their electron orbitals reconfiguring in quantum leaps. The ATP molecules that power your cells involve quantum electron transport. Life itself is a quantum process, even if we experience it classically. Your brain, processing these words, might be performing quantum computations we don't yet understand. The neurotransmitters crossing synapses are quantum objects. The ions flowing through neural channels tunnel through quantum barriers. The electromagnetic fields generated by neural activity are quantum fields. Whether or not consciousness itself is quantum, it emerges from a substrate that is fundamentally quantum mechanical. And extending outward from your body, quantum effects continue. The Earth beneath you is held together by quantum forces. The sun shining on our planet fuses hydrogen through quantum tunneling. Without quantum mechanics, the sun wouldn't shine. The stars visible at night are quantum engines, their light produced by quantum transitions, their stability maintained by quantum pressure. The entire universe is quantum, from the smallest subatomic particle to the largest cosmic structures. The difference between our real universe and the imagined one we've been exploring is not that one is quantum and the other classical, but that in one the quantum effects are hidden by scale and decoherence, while in the other they're visible and macroscopic. The moon-sized, quantum particles we imagined are just a way of making visible what's already true. We live in a quantum cosmos governed by quantum laws, existing as quantum beings. This realization that the everyday world emerges from quantum foundations is one of the most profound insights of modern science. The solid table in front of you is mostly empty space held together by quantum forces. The continuous flow of time you experience emerges from discrete quantum events. The definite world you perceive crystallizes from indefinite quantum possibilities through the process of observation and measurement. Even concepts we think of as purely classical have quantum origins. Temperature is the average kinetic energy of quantum particles. Pressure is the momentum transfer of quantum collisions. Color is the frequency of quantum electromagnetic waves. Hardness is the resistance of quantum electron clouds to compression. Every property of the macroscopic world has its roots in the quantum realm. As we contemplate this reality, that we already live in a quantum universe, we might wonder why evolution didn't give us direct perception of quantum effects. Why can't we see superposition, feel entanglement, experience quantum tunneling? The answer likely has to do with what was useful for survival on the African savanna where our ancestors evolved. Tracking the average behaviour of trillions of particles, what we call classical physics, was more useful than perceiving individual quantum events. Seeing definite positions of predators and prey was more important than observing probability distributions. But perhaps we're evolving new forms of perception. Through science, we've developed instruments that let us observe the quantum world, electron microscopes, particle detectors, quantum sensors. Through mathematics, we've developed languages that let us describe quantum behavior precisely. Through technology, we're learning to manipulate quantum states directly. We're becoming quantum-aware beings, able to perceive and interact with the quantum realm even if we can't see it with our naked eyes. The future might bring even more direct quantum perception. Brain-computer interfaces might let us experience quantum superposition directly. Quantum neural implants might allow conscious control of quantum states. Genetic engineering might give us senses that can detect individual photons, observe quantum fields, feel entanglement. The boundary between the classical world we perceive and the quantum world that underlies it might become increasingly permeable. Virtual and augmented reality could let us experience quantum effects at human scales, much like our thought experiment but as lived experience rather than imagination. You might put on a headset and see the world with quantum vision, probability clouds instead of definite objects, interference patterns in the air, entanglement threads connecting everything. These wouldn't be fantasies but accurate representations of the quantum processes actually occurring, just scaled up or slowed down to human perception. Education is already beginning to change to reflect our quantum reality. Children are learning about atoms and photons at younger ages. Quantum mechanics is moving from graduate physics courses to undergraduate, even high school curricula. Games and simulations let students play with quantum concepts, building intuition for superposition and entanglement. The next generation might grow up as comfortable with quantum concepts as we are with classical ones. Art and culture are beginning to engage with quantum ideas. Musicians compose pieces inspired by quantum uncertainty. Visual artists create works that explore superposition and observation. Writers craft stories that play with quantum themes, parallel realities, observer effects, spooky action at a distance. Quantum mechanics is entering our cultural consciousness, becoming part of how we think about ourselves and our world. Philosophy and spirituality are grappling with the implications of quantum mechanics for free will, consciousness, and the nature of reality. If the future is genuinely uncertain at the quantum level, not just unknown but undetermined, what does that mean for choice and responsibility? If observation plays a fundamental role in creating reality, what does that say about consciousness? If everything is entangled at the quantum level, what does that mean for individuality and connection? These aren't just abstract questions, but practical concerns as we build quantum technologies that might amplify quantum effects to human scales. Quantum computers might make certain kinds of prediction possible that seem to violate free will. Quantum sensors might detect thoughts before they become conscious. Quantum networks might create new forms of connection that challenge our notions of privacy and individuality. As we stand at this threshold, poised between the classical world we evolved to perceive and the quantum world we're learning to understand, we face choices about how to proceed. Should we try to maintain classical intuitions in a quantum world? Should we embrace quantum uncertainty as fundamental to existence? Should we use technology to shield ourselves from quantum effects or to amplify them? These choices will shape the future of our species and our planet. If we learn to work with quantum mechanics rather than against it, we might develop technologies that seem like magic: teleportation, time travel, faster-than-light communication. If we understand the quantum nature of life, we might cure diseases, extend lifespan, even create new forms of life. If we grasp the quantum basis of consciousness, we might enhance intelligence, share experiences directly, even upload and download minds. But we might also discover fundamental limits, quantum principles that constrain what's possible. The uncertainty principle might limit how much we can know, the no cloning. Theorem might prevent certain kinds of copying and backup. Decoherence might make some quantum technologies forever impractical. The universe might have quantum rules that we must accept rather than overcome.